I have a tendency to forget. Got it. And got it. Okay. And we are in day 4. And day 4, this is going to be our finishing up of everything. So so we're on page 58, I believe, in the book, which is tuning, use of filters, squelch function, AGC, repeater offset, memory channels, and stuff like that. Lots of details on how to operate a radio. So, okay. So the first thing we're going to say, what happens if a transmitter is operated with the microphone gain set too high? That's basically like doing this, and I probably sound kind of distorted. So in order to stop that from happening, you back away from the microphone or turn down the gain. In order to change a frequency, so for the sake of doing this, what we're going to do is I'm going to bring up something in just a minute called an SDR, but you basically have a keypad or a VFO knob. Even this little radio has a keypad right here. You can enter a frequency directly, or a VFO knob. VFO stands for variable frequency oscillator. By doing that, you change the frequency that the radio is operating on. One of the best ways to enable going to a location, a particular frequency, you have those buttons all the way down in the corner. In this particular case, I have a button that says VFO/memory. This radio has about 250 memories in it. Some of them have as many as 1,000. They can be programmed in a lot of cases via computer, which means you can just type it in and then download them into the radio. And then you can scan memories. You can say, oh, I need to go to memory 22. And memory channels are great because they remember all the offsets and all the codes and tones and things like that you want to use. Scanning function in an FM receiver. So that allows me to do things like this, where you probably see the frequency changing rather rapidly. This is basically scanning through a whole bunch of different memory channels to look for activity. The purpose of a squelch control, well, the easiest way to describe what squelch is if I pick a particular frequency, this is with the squelch turned off, and I'm going to switch microphones here. And this is with the squelch activated. This is with it turned off. So basically squelch basically turns off the receiver when there's nothing to hear. So that's what squelch does. It basically quiets the receiver when there's no signal being received. Repeater offset. Okay, so there are 2 ways of operating. There is simplex and there is duplex. All right, simplex is, let's say we pick a frequency of 28.450 megahertz, and we have 2 stations and they're operating on the exact same frequency. One station talks, and then immediately after, the other station talks. And because they're on the exact same frequency, what happens if they talk at the same time?
Cancel each other out.
They cancel each other out and nobody can hear anyone. And if somebody else is listening to both of them, they will basically hear the sounds of both of them, which gets a little confusing, at least on amplitude modulation modes such as single sideband. If these are FM modes, frequency modulation, what will happen is that these 2 signals will completely cancel each other, and this is known as a double. And what happens on FM is that nobody wins and you hear nothing. You just hear a lot of static, or squealing or screeching or some other horrible sound. So that's when someone says, hey, you know, we have to work to eliminate doubling on our repeater. That's exactly what that means. So this is known as simplex if they're on the same frequency. There's another way to do it, which is full duplex, which is channel A and channel B. And somebody's talking this way and someone's talking this way. And here's a person here and a person here. This is common on telephones where you can talk and hear at the same time. And this is known as full duplex. That's true full duplex, where you have signals being received and sent at the same time, and you can hear and speak at the same time and don't interfere. Now, there's another one that's called half duplex, which is typically what we do on the radio. It's commonly known as duplex, but it's not true duplex. And the way that it works is that you use two different frequencies. And when you are transmitting, let's say on frequency A, your receiver is turned off and you can't hear frequency B. And then when you stop talking, your radio can now receive frequency B. And the reason we do this is because very often this is actually a repeater. And this is you. This is your transmitter. And this is your receiver. So what ends up happening here is that a repeater is a very special device that when a signal comes in on frequency A, the repeater sends it out simultaneously on frequency B. Now, the nice thing about this is that if anybody else is listening on frequency B, they can hear what the repeater is doing. And what the repeater is actually doing is repeating what you're saying on frequency A, which means that the people who are listening to you could be way over here, or way over here, or way over here. So this difference in frequency is known as your offset. That is your frequency offset. So there are two things that you typically have to know. By convention, on the 2 meter band, which on our chart is 144 to 148 megahertz. The offset is plus or minus 0.6 megahertz. Another way to write that would be plus or minus 600 kilohertz. On the 70 centimeter band, which is 420 to 450 megahertz, the offset is typically plus or minus 5 megahertz, which basically means that whatever frequency the repeater is transmitting on, I am transmitting on a different frequency so that those signals don't clobber each other. So that the repeater can actually hear and transmit on different frequencies at the same time. All right, so that's known as a repeater offset. Now, offsets are not exclusive to repeaters. Offsets are also used, let's say, if we're listening on a particular radio frequency band, let's say 14.025 megahertz. This would be in the 20 meter band. And I have a station that's transmitting right here. And this station is in Zimbabwe, which is a fairly rare country to hear somebody transmitting from. Well, because it's a fairly rare country to hear somebody transmitting from, what would happen if the 2,000 people who were trying to talk to this station in Zimbabwe all came down on that exact same frequency? What would you hear, everyone?
Blah, 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 blah.
That's right. You'd hear basically just chaos. So what that station does is say, okay, in order to keep the peace, I am going to listen on 14.030 megahertz, for instance. And they basically set up a situation where they have an offset known as a split. This is a split frequency. Now, what happens if 2,000 stations are calling on the exact same frequency anyway? What's he going to hear? Just utter chaos, right? So what he'll typically do, what that station will typically do is say, I'm going to be listening from 14.030 to 14.040 megahertz or something like that, and everywhere in between. And essentially, his receiver will then be used to tune to any number of different frequencies in this entire range and pick out the strong signal and say, that's who I'm going to talk to. But at that same time, does that station ever want to change his transmitting frequency that everyone else in the world is listening to? And the answer is no. So this is known as a split operation. And one way to achieve this is by using something called RIT, or receiver incremental tuning. It allows you to change the frequency of the receiver without changing the frequency of the transmitter. So it allows you to separate the receiver and the transmitter. And this is one of the really good applications of it. And this is actually known as a pileup. So to be able to handle a pileup, that's when you would use something called split frequency operation. And the way to achieve it is by using the RIT. Now, some radios also have two receivers built in. Some older radios actually have a separate receiver and transmitter. You can use that as well. Another name for RIT, which is being able to adjust the receiver frequency without changing the transmitter, this is known as the clarifier. And it could simply be used just to, like, let's say that you're talking to another person and they sound a little bassy for some reason because you're tuned slightly off frequency, or they're tuned slightly off frequency. The clarifier is really designed to make them sound correct by adjusting your receiver frequency without adjusting your transmitter frequency.
By doing what?
It's basically just, it changes the receiver frequency slightly without changing the transmitter frequency so that they sound correct. It kind of clarifies their signal. Okay, let's see. The automatic gain control. Okay, so let's say that you're listening to a signal over time, and the signal that you're listening to is this, and this is as time goes on, and this is amplitude. And all of a sudden, your next door neighbor comes on, and the signal jumps up to here, right? But you were trying at this time to listen to something really, really quiet, and then all of a sudden, your neighbor comes on and blasts this gigantic loud signal, right? If you're listening to something quiet and you have your headphones turned, your volume turned way up, and you're trying to strain and listen to something, what happens when your neighbor comes on? What will happen to your ears?
Your ears will hurt.
Your ears will hurt a lot. So there's something called AGC. Well, gain is how much amplification you have in a circuit. Something called AGC is automatic gain control. And what it does is it says, okay, if I get a really big signal, I'm going to reduce the gain of the receiver so that the volume stays basically constant and it doesn't destroy my ears. And that's known as AGC, or automatic gain control.
So it modulates the sound.
It does. It basically, it reduces the sound by reducing the gain of the receiver. Okay. What is the advantage of having multiple receive bandwidth choices? Okay, so now what we're going to do is draw our frequency spectrum from 0 to infinity. So this is our frequency again. We're going to do a lot of frequency graphs today. So this is our single sideband signal. Here's our center frequency, and their single sideband could be the upper sideband in this case. Does anyone remember what the approximate bandwidth of that signal is in hertz?
Which one?
Single sideband, upper sideband.
6 kilohertz.
Nope, AM is 6 kilohertz.
Oh,
It's about 3 kilohertz.
3 kilohertz.
3 kilohertz. So a filter that is 2400 hertz wide would be a nice narrow filter for single sideband. So, because you can pretty much ignore the highs and the lows. And so a 2400 hertz wide filter would be a pretty good filter for single sideband. If I were listening to Morse code, which has a bandwidth of about 150 hertz, what about that 2400 hertz wide filter? What's coming through it? Well, you have the signal you're listening to, but what about all this other stuff too? That's all coming through also. And you don't really need to listen to all that other stuff. So we have a different bandwidth on our filter for Morse code. A nice, easy listening filter would be about 500 hertz. And in fact, most CW filters that you can install in a piece of equipment, a wide CW filter is about 500 hertz. If you go narrower, you can go down to 250 hertz. But then it starts to actually sound like you're listening inside a trash can at some point. So your good, your best filter choice for Morse code is typically 500 hertz. And for single sideband, it's 2400 hertz. Okay, so now we also have a button called push to talk. I
Can you
have one
remind
of
me what
those.
CW is?
Morse, that CW is Morse code,
Okay.
or Morse code is used to encode via CW, which is continuous wave. It's basically just turning a signal on and off. All right, a push to talk button right here where my finger is. This is my push to talk button on my handheld radio. I have a push to talk signal on a handheld microphone as well. If I'm using a digital communications method and I have to key the radio, the computer might actually have the push to talk button built into it and be able to key the radio. All right, so now we are moving to something called a transceiver. So a transceiver is a combination of the two words transmitter and receiver, and it is exactly that. So it's a box that has a transmitter and a receiver built into it. So very importantly, what happens when you transmit, considering that these two things are connected to a single antenna? What would happen if you transmitted and the receiver was not turned off?
You'd overload your receiver.
You would destroy your receiver. So inside the transceiver, you have a TR relay that separates the transmitter from the receiver so that when the transmitter is on, it completes this circuit and it isolates the receiver and thus keeps from destroying it. So that's known as a transceiver. So, okay, next, we also have something called a transverter. And what we're going to do is draw a circle with a big letter X in between. And we're going to have we're going to put 28 megahertz. And down here, we're going to put 194 megahertz. Okay, this is a special magic box called a mixer. And what a mixer does is that it is a nonlinear device, which when two signals are presented to it internally, it produces the sum and difference of those two different frequencies and puts them out on the output. So if I have 28 and 194, give me two things that are going to come out of it. If I have sum and difference, give me two different numbers that will come out.
202.
I got 222.
Oh, 222. Sorry, didn't
And-
put them underneath each other.
And what's the other one?
And the difference, so it would be 166.
166. So this will actually generate a couple of different frequencies. And in there as well will be the original 194 and the original 28 and a bunch of other things as well. So now let us say that this device is this device, which uses a mixer, is a transverter, which is a transmitter converter. That's what a transverter is. My original transmitter operated on 28 megahertz, and I want this device to be a 222 megahertz transverter. Well, so far so good, right? But what do I not have yet? What haven't I done? What other frequencies are there that I don't want?
All those other ones.
All those other
two.
ones. That's right. Those are ones that I don't want. Well, and it turns out that 194 and 166 aren't even ham frequencies. So I really can't transmit those. So let's put them on our frequency chart from 0 to infinity, amplitude and frequency. We're going to have one at 222 and one at 194 and one at 166 and one at 28. Okay, so what would I make in order to make sure that only the frequency that's here comes out and this one and this one and this one don't?
The limiter?
Close. Starts with the letter F.
Filter.
F like Frank?
Yep. I would build a filter.
Hmm.
And my filter would look something like this. Remember, we were talking about what makes a good radio versus a crappy radio? Filtering, filtering, filtering. I would try to build a filter that looked like this, where I had a pass band that would allow the frequency that I wanted to get through. And I would also have this reject band on the left-hand side, which blocked those frequencies by creating a very high impedance to block them from getting through. So we were talking a little bit, we were talking about audio bands, right? We're talking about speakers. Essentially, this is what a tuned cavity does. It has a resonance at a particular frequency. And just, you might remember from yesterday, there were two devices that we can use to make a resonant filter in radio, in electronics. What are those two things? There's one,
An inducer.
capacitor and
Inductor.
an inductor. And if we, depending on how we align them, if we go like this, that makes a filter that looks like that. If we were to instead do it like this, like this, and put them in parallel, we would actually end up taking this filter shape and inverting it. And we would have a band reject, where it would basically allow everything, but at some point it would block frequencies from coming through at the resonance point. If we were to rearrange this again, like this, again, that would invert it, and we would end up with a band pass filter. This is a band pass filter. So by choosing our capacitors and our inductors, that allows us to pick a frequency. And by aligning them in a certain order, that allows us to determine what that device actually does, whether it's a band pass or a band reject. Now, I can also draw it like this. Here we go. Let's pick blue. Okay. So now I have a capacitor that goes from here, the top, to ground. What do we remember about capacitors and AC? They tend to short circuit. So the higher the frequency goes, the more it will be shorted to ground. And if I were to draw this filter, it would look like this. So what frequencies would get passed through? Those would be the low frequencies. And this would be called a low pass filter. If I were to reverse these and make it look like this, the low frequencies would go down through the inductor, and the high frequencies would pass all the way through. And that would be called a high pass filter. So basically, by choosing my inductors and capacitors, I can change where that break point is, where it goes from being bad to good. And I can also change the shape of my filter just by moving them around. Which is why, because they're physical devices, a more expensive radio typically has better filtering. Okay, so now, what kind of filter would this thing up at the top be? So our choices are a low pass filter, a band pass filter, a band reject filter, or a high pass filter.
The band pass.
That would
Yeah,
be a
band
band
pass.
pass filter. That's exactly right. Because we've now selected those capacitors and inductors so that it passes just that band of frequencies. Very good. All right, so this is a transverter. And what's cool about a transverter is that very often a transverter works both directions. So signals that are coming in from the outside mix with that 194, and they produce 28 megahertz. So you can actually use your 28 megahertz transceiver as the basis of having a transverter and getting on a brand new band that you didn't have access to. Okay, next, what device increases the low power output from a handheld transceiver? That would be an RF power amplifier. So what is the power amplifying device in an amplifier? We talked about it yesterday. It looks like this. What is that?
NPN
That is an NPN transistor. Right. I could also draw one of these. And that would be a field effect transistor or a FET. Those are the most commonly used devices for power amplification today. They're all solid state. Now I could also draw something that looked like this. This is what we call our enrichment part of the class. If anybody happens to know what this is.
It's a tube.
That is a vacuum tube. That's exactly right. And there are certain reasons why you sometimes wouldn't want to use a vacuum tube. And this is actually on the general class exam. So if you're studying for the general as well, you will start to get to vacuum tubes. So you have your anode and your cathode. Notice they're called the exact same thing as in a transistor or a diode, are they not? And you have your grid. And they have different names for those grids. So basically you boil off electrons, a vacuum tube is full of a vacuum, which is nothing, and your electrons float across from the minus terminal to the positive terminal. And the grids allow you to control how fast that happens. And if you control how fast it happens, is current. So basically by putting a signal on the grids, you can change what the current out of the tube is, thus making a much bigger signal. Now, unlike a transistor will typically operate at, let's say, 12 to 24 volts, some high as high as 48 volts. A vacuum tube, because you have to actually have a fairly high voltage, will operate at between, let's say, 250 up to 3,500 volts. So what does that mean about something that uses vacuum tubes?
Dangerous.
Yeah, you basically have to generate, let's say 3,500 volts, right? That's enough to like really ruin your day if you stick your finger in and get a shock. So, okay. Which term describes the ability of a receiver to detect the presence of a signal? So what we're going to do is a little example here. Jan, you're good at this. I know you're
What?
good at this. Okay, I'm going to ask you to whisper something really quietly. Just whatever you want. Say something really quietly. Okay, could anybody hear that? Okay, because I actually couldn't hear it, which basically means that my ears through this path are not sensitive enough to hear it. That is the definition of sensitivity of a receiver. Okay, now here we go. Okay, what I'm going to ask is everybody to unmute themselves. All right, we're going to have some fun. So go ahead and unmute yourself. And on the count of 3, I want everybody to say your name. Right? All right, on the count.
Debbie.
No, on the count of 3.
Oh, sorry.
Okay, ready? Okay, ready? 1, 2, 3.
Steve.
Okay, I thought I heard Steve. And I thought I heard Debbie, right? So basically the ability to pick out one of those is known as selectivity. So I heard that. So, okay. So sensitivity is the ability to pick up a weak signal. Selectivity is the ability to separate a whole bunch of signals into something that you can hear. So let's say that what could you use to increase the selectivity of a receiver? let's say that you're listening to a frequency band that has a whole bunch of signals and you're receiving all of them. So this is our frequency, 0 to infinity. And here's our amplitude. And we're hearing a whole bunch of signals. What would be a way to improve the selectivity of your receiver?
The capability to reject other frequencies by having a, I don't know,
Filter.
pass filter.
That's right. Basically, we have a filter. If we're listening to Morse code, this would be like a 500 hertz filter. If these signals are actually single sideband signals, we could put a, let's say, a filter here that would be this wide. And we would reduce our cacophony from like 8 signals down to like 3. Which isn't enough, but you know, we're doing the best we can. So that's a way to improve the selectivity of your receiver, add filtering. Okay, where is an RF preamplifier installed? So here's our antenna. And here's our receiver. Okay, an RF preamplifier is a device that is designed to listen and amplify. If anyone has cable TV or anyone has like satellite TV, and somebody's ever come out and said, your signal's not strong enough, we need to boost the signal, you would typically put it as close to the antenna as possible. And that would be an RF preamp.
An RF what?
Preamplifier.
Preamplifier.
And the reason that you would do that is because, we're going to talk about systems now. Here we go. This is our system talk. Let us say that our receiver has the ability to listen, to hear anything. This is its sensitivity, minus 120 dBm, which is decibels compared to a milliwatt. So basically 120 decibels lower than 1 milliwatt, which is actually about one, let's see, it's not a pico, it'd be even smaller. 1 femtowatt. It's almost no power at all. I mean, it'd be 0.00000000000000001 watt. That's how much power is fairly typical of being able to be heard by a receiver, right? Which is why we don't bother writing that. That's why we use numbers that look like that. Okay, so now let's say that coming into the antenna, you have a signal of minus 110 dBm. Okay. Now, if you had no loss in your cable, you had minus 110 dBm here, what would you have down here? You'd have minus 110 dBm, and
Yep.
you would be able to hear your signal. But let's say that you don't have very good cable, or you're at a very high frequency and your cable loss is negative 12 dB. How big is your signal when it gets down to the radio now? You just add them together. So what's minus 110 and minus 12?
120.
Minus 22.
Minus 122. So is that above or below that threshold?
Above. Above.
No, it's below. Because remember, it's
Wow.
negative.
Oh, it's going down. Yeah.
It's going down.
Negative.
What will I hear?
Nothing.
No signal at all. Okay, so clearly I have a problem. So my solution here is, if I can put a preamplifier here that has a gain of, let's say, plus 5 dB, and it's sensitive enough to pick up things down to that are above 120, minus 120 dBm. Okay, well now I have a plus 5 dB thrown in here. Now add them up again. Minus 110 plus 5 minus 12. What do I get?
Minus 117.
Minus 117.
Which picks up.
And I'm good. And now I can hear it again. Okay, but now what I'm going to do is I'm going to take this preamplifier and I'm actually going to move it and say, I don't really want to put something out on my tower, because that means it has to be weatherproofed and costs extra money. And so I'm going to put it down here in my station. So I have a plus 5 dB preamplifier, And again, its sensitivity is minus 120 dBm. Does this work? Yes or no?
Yes.
It doesn't. Why not?
You're amplifying the noise.
That's right, because by the time it gets down there to it, I have taken this away and I'm now where? Minus 122. And I already said that this has a sensitivity of minus 120. So the receiver preamp, the RF preamplifier that I just put in, can't hear it either. So basically what I'm just doing is making the noise louder for my receiver. So that's why when you go and have a cable TV hookup, they might say, oh, we need to go and put an amplifier box out at, an amplifier out at the cable box out on the street, because you can't amplify what you can't hear. If you can't hear it in the first place, there's nothing to make louder. Okay. The name of a circuit that generates a signal at a specific frequency is called an oscillator. Basically, if you think about an amplifier makes something big, right? It makes something small into something big. But what happens if you take something that amplifies something and you take part of the signal from the output that you just made bigger and put it back into the input and make it bigger? And then it starts to oscillate and you get, we've all heard that on a speaker system or a PA system. That's known as an oscillator. Sometimes it's intentional, sometimes it's not. If it's intentional, it's actually called an oscillator. And by choosing the components, they can either be capacitors and inductors, because that makes a resonant circuit, or by choosing a device that looks like this, which is it looks like a capacitor, but it actually has a piece of quartz inside it. Anyone know what that would be called?
Crystal.
That's a crystal. Yeah, physically, it is a crystal that actually has a piece of rock in between that vibrates. That's known as a crystal oscillator. By using those devices, we can actually generate a frequency that we want.
So when you started this, Scott, you said oscillator and you gave the explanation. Will you say that again? Amplifies?
Well, basically an oscillator makes a frequency of a specified, a specified frequency. It makes a signal of a specified frequency. I mean, an oscillator is essentially like an amplifier gone wrong, unless that was your intent. Sometimes we want to make a frequency. Sometimes we will pick our inductor and capacitor so that we make a frequency of 9.026 megahertz. Well, we can do that by going back to our resonant frequency, where our frequency is 1/2 pi square root of LC. That's the resonant frequency of an LC circuit, which we briefly covered yesterday, but I said I wasn't going to get too far into. But this is the this is the basis of tuned circuits.
Scott, can you say what's a real world scenario on why you would want to ever use an oscillator?
Oh yeah, sure. So let's say I had a signal coming in and I have one here. This is from my radio, and I want to make 194 megahertz oscillator so that I can produce 222 megahertz, right? And this is the real world, because it's in a radio. I have to make a frequency of 194 megahertz. How do I make a frequency of 194 megahertz? I mean, that's basically a signal that goes like that, 194 million times every second. How would I do that? Another real world application of this is something called an atomic clock. Right? This is what we use for timekeeping. There's another one that's a quartz crystal clock. Right? If everybody likes their watch, you like to keep accurate time, You have to generate an accurate frequency in order to do that. Other applications of it, for instance, are there any musicians? Does anybody know what 440 hertz is?
A.
It's A above middle C. Okay. How do you generate a frequency of 440 hertz to tune your instrument?
Tuning fork.
You could use a physical tuning fork, but there's also electronic devices that will output. Does anyone have an electronic tuner that generates a frequency?
Mm-mm.
Yes, but they're crappy.
Well, okay. But a
But
440
I have
hertz.
an electronic tuner, an electronic item that tells me if my cord is on that frequency. It doesn't generate a frequency, but it knows if my frequency is there.
Right. Well, but how does it know that? It either
I don't
counts it and
know.
measures it, or it compares it against a reference. Well, if it's comparing it against a reference, where does it get the reference from? It makes it inside. So real world applications of an oscillator.
Hmm.
Okay.
And that's how a PC generates its clocking.
That's exactly right. Thank you, Russ. So yeah, that's how your computer knows how many clock cycles to do. Which of the following describes combining speech with an RF carrier signal? Combining any signal with an RF carrier signal is known as modulation. Okay, so now we're on to page 62, which is what happens if things go a little bit awry. Which of the following can cause radio frequency interference? If you have fundamental overload, basically you're driving past a big TV tower or a radio station, and your car radio picks that station up on all frequencies. That's basically fundamental overload. The receiver just can't handle it, even if it's not on the same frequency. A harmonic, for those of you who are musicians, a harmonic is a multiple of a given frequency. If we were to draw a vibrating string, for instance, we would have this on that vibrating string. If we fretted it properly, well, you would also have different, you would also have something that looked like this. You would also have something that looked like this. You would also have something that looked like this that could exist on that same vibrating string. Those are all harmonics. They're frequency multiples. So if the original frequency was, let's say, an A at 440 hertz, you would have twice that. You'd have 880. You'd have 3 times. You'd have 1320. You would have 1760. And those would typically be lower and lower amplitude, but all of those harmonics could exist on that same vibrating string. The same is true when you're building an amplifier. You basically can have integer multiples of a frequency. So if I have an amplifier or an oscillator that makes a signal at 10 megahertz, I might also get something at 20 and 30 and 40 and 50. And if I were to plot these out, the big one would be the original one, but then the first and the second and the third and the fourth and so on. How would I get rid of the ones that I don't want, everybody? What's that thing called?
Filter.
That would be called a filter. It could be a low pass or a band pass, depending on how I was building it. And why is this important? Why do we even need to know this stuff? Because we are allowed to build our own equipment. And in building our own equipment, the FCC has guidelines for the amplitude of harmonics that are generated by your transmitter. And in fact, they are measured in units of decibels. So these harmonics typically have to be 50 dB to 60 dB down, depending on where they are from the fundamental, which means if I have 1 watt here and I have 60 decibels, this has to be 0.000001 watt of power. So if I don't have good filtering, all of a sudden I'm putting out signals that I'm not supposed to. There's also something called a spurious emission. This can be caused by other things that are going on in your amplifier circuit, because every amplifier can act as an oscillator. There might be something that's not harmonically related, like one over here and one over here. Spurious emissions also have to be knocked down by filtering to those levels that make it legal. Which of the following actions did you take if your neighbor tells you that your station's transmissions are interfering with radio or television? Well, the easiest thing to do is stop transmitting. But the next thing to do is make sure that your own stuff is actually not interfering with your own radio and TV, because you don't know if it's your problem or their problem until you ensure that it's not your problem on your own TV. If you have cable TV interference, those little cable DV connectors tend to unscrew over time. When they unscrew, they get loose. When they get loose, signal can leak in or out, and then you get interference. So the first thing to do is make sure that your cable TV connections, like on the back of your TV or on the back of your cable box or on your Wi-Fi router, are all nice and tight.
Scott, what is real world if it's their problem and they don't feel like fixing it? Do you
Okay, we're
stop?
getting to that. We're getting to that right now.
Yeah, that's a good question.
We're getting to that. Okay, so what would cause a broadcast AM or FM radio to receive an amateur radio transmission? Basically, if we have an FM radio that is designed to operate at 90 to basically 110 megahertz, and we are transmitting up here at 146 megahertz. Is that FM radio supposed to hear you?
Nope.
It is not. But what happens if it does? What is pretty bad inside that radio if that's the case?
It's selectivity.
That's right. It's selectivity, and probably it has crappy filtering. So one thing you can do is you can put a bandpass filter on that radio if you happen to really want it. So basically it's unable to reject the strong signals outside of the band. One thing to do, again, you can put a filter on the outside of it. If it actually has an external antenna, you can actually install a filter.
On the radio that.
That can't
you're
reject it.
linking through to that radio, and that's the radio that needs the filter.
Correct. The other thing to do is if you have a VHF transceiver, and let's say this goes the other way. You have 99.1 transmitting at 100 kW right next door, and you're hearing it on your radio. What can you do on your radio? You can install a bandpass filter to block it out. And then this would be a band reject filter. Conceivably, it could actually look like that too, which is also known as a notch filter. So you could notch out that other frequency if you wanted to block it out. So it works both directions.
Todd, I was wondering why would it we be able to pick it up if you're listening to a higher frequency? Is it because of harmonics or something?
No, just because there's so much RF that your internal circuitry is just picking it up. It's getting into everything.
Okay.
I mean, basically, if you think about it, I mean, just because you've designed a certain circuit to have, let's say, 60 dB of rejection, right? Well, 60 dB is not infinity.
Yeah.
Right. And if it's a big enough signal, you might still get a little bit sneaking through down here. So that's just practical real world engineering stuff. So does anybody remember having a wired telephone owned by the Bell system? Raise your hand if you do. Okay.
Yeah.
All right. So it used to be that since the phone company was the phone company, that if you interfered with a wired telephone, you actually typically rented the phone from them they would actually come out and put a filter on your phone to keep it from getting interfered with, because it was their phone. So they would actually come out and do that.
Bypass filter is going to be at the base of the transmitter
you.
or at the antenna?
Thank you.
On which one? Like for a telephone?
No, on the radio, for instance, the bypass filter.
It doesn't really matter, honestly. It would be probably close to the radio, because you're trying to block something. You're not trying to amplify something. So the only reason you would ever put something way out at the antenna is if you had a preamplifier that you were trying to amplify a signal as it was coming down.
Understood.
Okay, well, we're talking now, we're answering that question. What happens if there's another something or other that you're interfering with and the neighbor doesn't want to do a damn thing about it? So let's say that I have me and I have them, and my transmitter is legal. I verified that it's doing exactly what it's supposed to do. And they have a TV that is, every time I transmit, their picture gets all screwed up. This is a Part 15 device. A Part 15 device is an unlicensed, unintentional radiator, or an unlicensed device that, as an electronic device, must receive, because it's unlicensed, must accept all interference caused by other licensed services. Well, ham radio is Part 97. That is the part of the FCC rules that governs amateur radio. Part 15 is an unlicensed device, right? So who's in the right and who's in the wrong if I am interfering with that?
They are.
They are. Now, the other part of it is that, let's say that this TV is for some reason electrically noisy and it is interfering with my ability to listen on my frequencies. Who's at fault?
They are.
They are still, that's right, because they're interfering with a licensed service. So Part 15 includes everything that isn't licensed. Your laptop is a Part 15 device. Your power supply that powers the laptop is a Part 15 device. Your LED lighting is a Part 15 device, right? Your microwave oven is a Part 15 device. You know, your television, in this case, my exercise bike, those are all Part 15 devices. So they are unintentional radiators. So if you are interfering with somebody else's Part 15 device, or if they're causing interference to you, you work with your neighbor, right? Because you try to keep things on good terms. Inform your neighbor about Part 15 and the fact that, you know, that they're really at fault. You've got your license and you're operating legally. You verified that everything's good. And you know that because you went through your entire station and you verified that all your connectors are tight and you're not generating any spurious emissions on frequencies you're not supposed to. So basically, you did everything right. You're following the rules and it's their fault, but you're still going to try to help.
Hey, Scott.
Like Hatfield and McCoy's.
Yeah.
When you first set up your system, and let's say that is happening then with a neighbor, and you say, I've done all this stuff. When you first set up your stuff, do you set it up with, I mean, do you send something in? Because in my memory, I'm hearing you don't have to do any of that in the
Correct, you don't.
you know.
That's, well, okay. So let's say you were applying for a television station license, right? When you set up your TV station, you probably have to have an FCC inspector come out and look at it, right?
Right.
Okay, what are we doing when we get an amateur radio license?
Just talking to people.
No, but I mean, what are we actually doing? Why do we have to learn all this stuff?
Because we're sending stuff out, we're transmitting.
But more importantly, we are learning all this stuff preemptively. That's
Right.
why this test is so technical, because because it allows you to go ahead and say, all right, I'm going to put a station together and I am the one who's ultimately responsible for it. It doesn't have to be inspected by anybody. I am now a qualified person to put together a station. I'm not going to bother the FCC. I don't have to bother the FCC. It's assumed that by going through the process of learning all this, I now am qualified to do this. And that's why it's not, as I say, this is not an appliance operator's license. This is an amateur radio license that allows you to build a station and actually use it. So, okay. What might be a problem if you report that an audio signal through a repeater is distorted or unintelligible? Well, there's a couple of reasons why you could be unintelligible. If your transmitter is off frequency, FM sounds really bad if you're off frequency. Your batteries could be running low. You can also be in a bad spot, and thus your signal is very weak. If you have RF feedback, so one thing that's important to note is that every antenna is a piece of wire. Therefore, every wire can be what?
An antenna.
An antenna, that's right. So if I transmit a signal out here and it generates an RF field, right? Radio frequency field, and I have let's say a wire connecting my speaker or my microphone to my radio, what can happen on that wire? Here's my RF energy. What can happen to my wire?
Oscillate with the frequency.
Yeah, it picks up the radio frequency. Well, if that somehow gets into this wire and it mixes with my audio signal, I basically will get distortion coming out of the radio, and people will say I'm all distorted. So there's something that we add to this. And this is a filter. You can put a filter that would basically filter out the RF and allows just the audio to get through, and everything's better.
Or we can just use shielded wire, right?
Sometimes. Sometimes it works, but let me ask a question. What's a shield made of?
Wire.
Wire, that's right. So sometimes it works and sometimes it doesn't. And sometimes if we do that, we actually take our entire cable with shield and all and run it through a ferrite choke, which basically collects the RF energy on the outside and causes it to make a magnetic field that then gets burned up as heat in the choke, which is something that we're going to get to also. If you're told your FM handheld or mobile transceiver is over deviating, you back away from the microphone. Okay, so now we're doing meters, testing, and things like that. So I'm going to bring up a picture of that while we're talking about that. Which of the following measurements are commonly made using a multimeter? That would typically be voltage and resistance. Those are the most common. A voltmeter is used to measure volts. An ohm meter is used to measure ohms. So that would be resistance. And an ammeter is used to measure current. So if I were to go to Harbor Freight,
Ooh,
oh, Harbor Freight's great for certain things.
no.
Yeah, it is. It has its purpose. All right. So a Harbor Freight has its purpose. All right.
Taking money out of your pocket. That's what it's.
Well, that too. Well, but let's say that they have don't miss these great coupons, and one of the coupons is a free multimeter. All right. If we zoom in on this multimeter, what we will see is that it has DC volts, DC amps, AC volts, and ohms, and it's also a transistor checker, all for the low price of $6.99. And sometimes it's free. So how is this different from a Fluke 87, which is what I use at work? Besides the fact that the Fluke 87 is $500. How are they really different from each other?
Fluke
Measure
survived.
higher voltage.
Well, actually, you know what? If you look at this Harbor Freight meter, you will see that it says right here, DC volts, 250 volts, and under AC, it has a 250 volt rating. And some of these small meters will actually say 750 or 1,000 volts. My Fluke also says 750 or 1,000 volts. So how are they different? One
Well,
of them,
there's different ratings. There's different category ratings, Cat 2, Cat 3. That one's a Cat 3, the other one was a Cat 2.
yeah,
And so it's rated to different levels. You also need to make sure that they're like certified on the
Yep.
back so
That's
that they
right.
don't blow up. I've
Yep.
seen them blow up before.
you have, okay. Well, yes, and in fact, this meter, I would use this to measure 24 volts. I would probably also use this, and I have, to measure 120 volts out of my wall socket. I typically will wear gloves when I'm doing it. This is what I use at work. This is rated to 1,000 volts, and it really is rated to 1,000 volts. I would actually trust this meter to measure 1,000 volts.
Fuses are $11.
Yeah, they are. The fuses are more expensive than this meter. So, okay, ensure that the voltmeter and leads are actually rated for use at the voltage is being measured to keep you from having a meter blow up or from dying. Okay, so how does an ohm meter work? Everybody, what is Ohm's law? Give me Ohm's law, everybody.
Equals I
E
times
equals
R.
R.
E equals I times R. Okay, so if I have that and I have a resistor and I take this and I put an E across it, what will I get? What will start to flow through the circuit?
Current.
I will get a current. Okay, so if I have a calibrated voltage and an unknown resistor, what will I get coming out of it? I will get a value of current. What an ohm meter does is it puts a voltage E, which is a known voltage, across the circuit, and it measures the I, and it says R is equal to E divided by I. And it says, okay, I know my E, I just measured my I by measuring the current, therefore I know what my R is. Now, the tricky thing here is that it has an E built in. It has a battery built in, which means that in order to actually calculate the resistance properly, you have to have no other sources of voltage in your circuit, which basically means that when you're measuring a resistor, it has to physically be separated from the circuit that you're testing, or the circuit that it's wired into. So you may actually have to remove it from the circuit. And at the very least, let's say that there is a battery in the circuit that goes like this. Somewhere in the circuit, you're going to have to take that battery out in order to keep from getting a bad reading, at the very best, getting a bad reading, and at the very worst, blowing up your meter.
And if you can't do that, if you can't remove the battery or remove the circuit entirely, then it's no use using an ohm meter.
Pretty much, yeah, because you might actually be, measuring the resistance of a bunch of other things. Like there might be some transistors in there. And
what if you could use your voltmeter to prove that you have 0 volts in the system?
It's still, even if, let's say you have this battery that you took out and you want to measure this one resistor right here. Right? Let's do that. You want to measure just that one resistor. Well, you hook it up and basically it's a voltmeter. It's a voltage being across it. What else is in parallel with all that other, with that one resistor?
All the other resistors.
All the other stuff. So you're really not measuring the resistance of that one device. You're measuring the cumulative resistance of the everything circuit. Which is why if you're testing one particular thing, you really need to lift one lead off of it or take it out of the circuit.
Does it say in the material, be sure the circuit is not powered?
That's
Is
right.
that the same thing as removing?
If you remove the battery, it doesn't have any power.
But if it's in the wall, you can't remove the battery,
Then you unplug it.
And unplugging it is the same as removing the battery?
Yep, it's basically just removing the voltage source.
But, okay.
Well, I mean, if it's powered off of 120 volts and you unplug it from the wall. Now, it might also be that, let's say it's a power supply and it has a big one of these in it.
Mhm.
That's a power supply with a really big capacitor. Well, if this charged up and this does not have this across it, which is a bleeder resistor, then you might not get a good reading either. Your circuit will still be charged. This is known as a bleeder resistor, which is supposed
Is
to
that like a
discharge.
laptop that you would unplug from the wall, but yet still has a battery in it?
Yeah, I mean, actually, if you've unplugged your, let's say your power supply on your, for your laptop, if it has a little LED on it, notice that the light fades gradually. If you have an LED on it, that's actually the capacitor inside bleeding off through a bleeder resistor, which is why it doesn't just turn off immediately. If depending on whether it's hooked to the computer or not.
Okay.
Another one way to blow up a multimeter is if you attempt to measure voltage with it on the current setting or on the resistance setting. So basically, if you set it up wrong, you can basically destroy your meter. Another really good way to destroy your meter is if you set it up to measure amps and you put it directly across a battery. Essentially, what this is internally is a short circuit. And depending on how it's built, it's basically looking at how much current is flowing through. Well, how much current is flowing through there if there's no resistance?
Oh,
All of it, yeah. So very often, somebody mentioned something about fuses. When I go and buy a Fluke multimeter, it actually has in the back of it a spare fuse, just for such an occasion when I accidentally hook it up to the wrong thing. And then it basically pops the fuse and I can go and buy a replacement $15 fuse for it. If I have a cheaper multimeter that doesn't have a fuse, what happens is that I do something called letting all the smoke out in a large cloud. Does everyone know what smoke is?
Mm-mm.
The magical component that's in every electronic device. It's
Just add power.
It's the magic stuff that makes every electronic device work properly. And once you let the smoke out, it doesn't work anymore.
Every technician has the same word for that smoke too.
That's right.
This is the family channel, but I won't repeat that.
Yeah.
Fumes?
No, it's smoke. Well, we let the smoke out.
I was thinking of the word.
Yeah.
You know the word. I'm not going to repeat it.
What is probably happening when an ohm meter connected across an unpowered circuit initially indicates a low resistance and shows increasing resistance with time? Okay, so we're going to have a mystery circuit right here. And we're going to represent this with a question mark. Okay, so now an ohm meter, again, consists of a battery and an ammeter, and we're going to connect it to this mystery circuit. So what happens is that we measure by using Ohm's law, E equals I times R. R is equal to E divided by I. So let's say that our resistance is initially really, really low, which means we have tons of current flow. And then as we get down to a certain point, the current flow goes all the way to 0. Well, what's actually happening inside this box, which is a mystery box, is that we have a big capacitor. And what's happening is that as the capacitor charges up, it can no longer take any more charge, and then we have no more current flow. So over a period of time, we see something that looks like this. We have our current versus time. It starts off very big. We go through our math and we plot our resistance. Resistance starts off at 0 and goes to infinity. This is actually the sign that there's a big capacitor in the circuit that you're testing out. An instrument used to measure electric current is called an ammeter. An ammeter, again, is in series with the circuit. unless you have a clamp meter. A clamp meter looks like this. This is like a donut, and that donut collects a magnetic field that's being made by the current flowing through the wire. And as that happens, it generates a current and a voltage that you can then measure indirectly, which is really useful if you, let's say you have a really big piece of wire and you can't disconnect anything to insert a meter. So that's an inductive ammeter. It uses the inductance of the coil to couple them together.
Is there a connection between amperes, amps, and amplitude that I'm missing?
Not amplitude, although.
No, but when they both will use A sometimes. So
yeah, not so much.
they don't
amplitude.
come from the same base. They're
Am-
different.
Yeah,
Totally.
amps and amperes. That's actually named after, actually named after ampere. Amplitude is just size. And maybe there was some connection at some point in time. I'd have to look it up.
That's okay.
Okay, when you're soldering, you use something called rosin core solder. Rosin is the same thing that you put on the bow for a musical instrument. If you burn it, it actually cleans the surface of whatever you're soldering. So rosin core solder is basically the stuff that's in rosin is the stuff that's in the core of the solder that we're melting, and it causes it allows you to deoxidize the surface. A cold solder joint, typically a solder joint looks nice and shiny if it's done right. If it's a cold solder joint, that basically means that it's not a good electrical connection, and it looks kind of dull and grainy. And it might work electrically until you decide that you want to take the radio off somewhere or your piece of electronics somewhere, and all of a sudden it doesn't work because it either got vibrated or something, or the temperature changed and things shrunk and it's no longer an electrical connection.
Scott, are most hams actually soldering circuits and adding filters, or we just go into Amazon?
It depends what you're doing. As far as making antennas, I solder all the time. It totally depends on what you do. Typically you're not going to be building your own filters, but you certainly can. There are enough kits out there, you can still build from those. Okay, let's see, we're into operating procedures next. Okay, so now we're into how to actually do stuff on the air. Okay, a station that receives a signal and retransmits it simultaneously. This is known as a repeater station. There are several different stations that can do this function of repeating and automatically retransmitting. A space station is anything 50 kilometers up or higher. That's a space station. A space station can automatically repeat signals. There is something on the International Space Station, which is a Kenwood radio, which is a repeater that has been set up there. It's a mode UV, so it's UHF upward and VHF downward. And if you send a signal up on UHF, it will come down on VHF. And that's known as mode UV. It's a UV repeater. And that's actually 200 miles up in the air, whipping around the earth. An auxiliary station is basically a station that's used to link two different radios together. So that can be like on a mountaintop where I have a signal that's coming here and it's being retransmitted to another repeater somewhere else. And that would be known as an auxiliary station. And yeah, quick break in just a minute. Okay, and again, a space station is any station 50 miles up or 50 kilometers up or higher. Repeater offsets on the 2-meter band, plus or minus, as we discussed, 600 kilohertz. This is actually important to memorize. 70 centimeters, plus or minus 5 megahertz. And there's a dividing line on each of these bands for whether you shift up or shift down. Something called CTCSS, also known as PL, if you work for Motorola, which is known as private line. It's a sub-audible tone that's transmitted along with your voice. And what it allows a repeater to do is if it gets a signal with no CTCSS coming in, and it has a CTCSS repeater set up, it will not open up the squelch and it will not allow anybody to hear anything. So you won't be heard. If you have the proper CTCSS tone, then you will be heard. And everybody will be able to hear you because the repeater is now retransmitting the signal. There's also something called a DCS, which is a digital coded squelch, which is kind of like a modern version of the CTCSS. It's basically a digital code that's sent along with your signal that allows the repeater squelch to open and allows the signal to be sent. If you have the improper offset set up, so let's say that I'm transmitting, the repeater is transmitting on 146.72 megahertz. My signal going into it has to be 146.12 megahertz. If the repeater has an that's if the repeater has a negative offset of 600 kilohertz. If you have the wrong offset, nobody will hear you because you'll be transmitting on the wrong frequency. The repeater could also be set up for a CTCSS of 100.0 hertz. If I'm not transmitting that, or I'm transmitting the wrong one, nobody will hear me. So those are the most common things that can go wrong when no one can hear you. So if I am, let's say there's a station that's on 146.12 transmitting, I might be way over here and I can't hear the repeater very well. But if we're really close, I might actually be able to listen on the other frequency. And then there's something called a reverse split, which basically allows me to flip my receiver and transmitter freight channels back and forth. That allows me to listen to the actual transmit frequency instead of the person who's transmitting. And that would be also known as listening on the repeater input frequency. It's the same thing as reverse split. Listening on the input. If the repeater user says your transmissions are breaking up, that means you're too loud. You're basically, on this radio, you don't have a microphone gain control at all. What it means is you basically take it and you move it further from your face. And that reduces the amount of signal going in. How to call another station? Well, the easiest way to identify yourself is just by saying N7JI on a repeater. You just give your call sign and that indicates that you're there. If I'm calling Roberta, for instance, and I see Roberta has a call sign of KI7MKK, and I want to call Roberta, I would just simply say, I'd key the radio and I'd say, KI7MKK, this is N7JI. That's it. And Roberta, how would you reply? You're muted, Roberta. Nope. Okay. So Roberta would reply by saying N7JI, this is KI7MKK, over. If you're on the same frequency, that would be known again as simplex. And what's a point of using simplex? That is if you're pretty close to each other and you don't need to use a repeater, or a repeater is a resource. And if you're close enough to each other that you don't need to tie up the resource, which someone else could be using, unless there's some compelling reason that you want other people to hear you, you should just switch over to simplex and go point to point. And the national simplex calling frequency, this is something that everyone has programmed into their radio. Most people who are driving, if they have a radio in their car, will scan across this frequency as well. 146.520 megahertz all over North America. This is the national simplex calling frequency all over US and Canada, pretty much anywhere you go. So this is something that everyone should commit to memory. It's right smack in the middle of the 2-meter amateur band.
Is that for emergency use?
That's for everything. If you are in a place where you don't know where the repeaters are, you don't know what frequencies they are, there will probably still be somebody listening on 146.52. It is one of the easiest ways to raise just anybody somewhere. Okay. Break time. Good
Quick
5-minute
question.
break? Yes.
Can you use repeaters with CW?
Well, okay. The question is, when you say CW, how so? I mean, if you think of it as like audio CW, like if I go and I send like audio Morse code over a repeater, yes, you can do that. And in fact, that is one of the ways that a repeater will identify itself, is by sending audio modulated Morse code. Or I guess it's called MCW. That's not really MCW. It's essentially Morse code over a repeater. But repeaters are FM. So you wouldn't ever be able to send true Morse code over a repeater. It would freak it out. But yes, you can send audio Morse code over a repeater. And in fact, we actually do classes and practice over our local repeater using that. I basically take a Morse code. I take a code oscillator and I take the speaker and I stick it right next to my microphone and I just send Morse code.
So one more quick question before we go. Going back to RF preamplifiers.
Yeah.
We said that you would want to put it as close to the antenna as possible,
Yep.
not close to the receiver, because then you'd be amplifying noise.
Right.
So
You could
physically,
conceivably lose the signal before it ever gets down to it.
right. So physically, where would you put that RF preamplifier? Actually on the antenna wire?
Yeah.
Okay.
So it would be called like a mast mounted preamplifier, and it would look like, let me see if I can find a picture. Here we go. A mast mounted preamp. And notice what you see right here, that this is basically now what looks like a weatherproof case, weatherproof connectors. And the reason it's weatherproof is because it's designed to go outside.
If you ever use the dish network, the amplifier is in the back of the dish at the end of the feed horn before it comes down into the house.
Yep. For that very
Is that
same
a
reason.
requirement in general or extra for learning Morse code?
No. Although I do love Morse code, I use it all the time. There's no requirement to do it. That went away in 2006.
What do you use it for?
I use it all the time to talk to
But-
other people because it's fun.
Okay.
And I've used it since I was 15 years old, and I happen to be pretty darn good at it. So not to toot my own horn or anything, but I really enjoy it. I can go fast, and that's one of the things that it screams radio to me.
It
So-
also allows you to talk in
To other
marginal conditions.
And because there's no accent, you can talk to people in other countries without having to deal with not being able to understand their accent and vice versa.
Is it in English worldwide?
Basically every language translates to Morse code somehow. So like if I'm working somebody in Japan, English letters are not part of their alphabet, right? But if you look at a Japanese QSL card and call signs, like we'll go here and I'll share this. And JA1NUT. Let's go to Duffy. Oh, I'm not logged in somehow. That's crazy. JA1NUT is a very active ham in Japan. But notice Notice that it's all written in English. And in fact, his call sign is in, English, or, the standard English alphabet. Every country in the world, no matter what language they speak, call signs are in English. So like, let's see, UX5UO. That's Gennady in Ukraine. He's actually a QSL card printer. So, if you were to look at it, his name, they obviously are in Cyrillic, but his call sign is UX5UO, and that translates to English. If somebody's going to send a message, this is one of the reasons that we use something called Q signals. We could say QTH, right? Because you could say, my location is. In English, it would be my location is. In Spanish, it wouldn't be my location is. It would be estoy en, right? Or vive en. So it's totally different, but that translates to a simple 3-letter Q code, which is QTH. And every ham who does Morse code around the world basically understands the exact same thing. That translates to whatever in their own language. So there are characters in Morse code that don't fall within the standard A through Z and the punctuation and 0 through 9. But those are like, there's like an enye in Spanish, and there are some Swedish characters, like an A with a little halo over it, or a U with an umlaut in German. There are Morse code characters for that, but most people don't know them unless they use them all the time. Like, I don't know them. And what's weird is when you're hearing two people speak in Morse code Swedish to each other, they're using English letters to speak Swedish. And then on top of that, they're throwing in the specific Swedish letters as well. And then you don't recognize those at all. So. Kind of a language unto itself.
Hey, Scott.
Yeah.
When we after we take the exam,
Mm-hmm.
God willing, we all pass.
Mm-hmm.
That are registered to take the exam. How long does it normally take for the FCC to generate our call sign?
If it's on a weekday, it's within an hour usually.
That's cool.
Yeah. It could be a few hours if things are slow.
So worst case scenario, by Monday, we would have our call sign and we'll be ready to go.
Probably this afternoon. Yeah. Honestly, probably this afternoon. All right. So okay. All right. Z signals. Z signals are only in the military.
Wait, didn't you say we're taking a break?
Yeah.
Did we?
Yeah.
And we talked right through it?
I did.
Oh, okay.
Some people started asking me questions. I can't tell, do you guys want another 5-minute break?
Yeah.
Yeah. Okay. All right. A real 5-minute break.
Hey, for anybody who's still alive, how many of you guys are in Florence and you're down to like get together after the exams and everything and really learn how to figure out these handhelds together?
I'm in Eugene, but if anybody in Eugene wanted to mess with their radios, I'd be interested in sort of seeing if I could talk to them. I don't know. I think I'm too, so I could kind of like do it myself too, but yeah, I'm in Eugene.
Just hold it down. Okay. I'll do it. Scott, are you still on there?
I think he went to a break.
Yeah, I think. Does anybody know how many people are taking the class?
I don't know, but I keep seeing like 36 people showing up on the participant section.
Oh, yeah. Okay, that's probably the number that are taking it. This is Frank. This is Alex's grandfather. It's been it's great to see so many people taking a class in ham radio.
Well, I'm not taking the test. And Frank, I don't know if you're missing your weeks. Next week is the Willamette Valley Club meeting.
Next week, Saturday after this Saturday is the test session, right? Oh,
No,
you're
no, no, no,
you're
no.
talking about the Willamette Valley DX Club?
Yeah, you said it was going to be next tomorrow. It's not tomorrow. It's a week from tomorrow.
Yeah, whenever it is.
I'll be there though.
Yeah,
A bunch
me
of us
too.
are signed up to take the technician test tomorrow. I know some people would.
Yeah, I'm signed up to take it tomorrow at 2:30.
I feel like mine's earlier than that, but I'd have to check my email to be sure.
Has Alex been taking the test, the practice test?
She's been taking practice quizzes in the different segments in the what's the study manual. It's not ARL, it's the other one. We couldn't get a hold of the ARL one, which is the one I like. But there's that one, it's a smaller format.
And ham study?
I don't
Hi,
know.
Frank.
It's Stu, somebody. Hey, Scott, did you get the information that I sent about the Oregon Tualatin Valley test session?
I don't remember. I've been a little discombobulated. I think I did.
Yeah, I think I sent it to you either yesterday or the day before, and I don't have it with me right now, but that's the one Alex is signed up to do, so she'll have a week to study.
Going in person? Yes. All right, so if you want to do an exam in person, the OTVARC exam, let's see.
First Saturday of the month, 9 o'clock.
Are you guys, Russ, you're an OTVARC member, right?
Yeah.
Is it a pretty big club?
Fairly good size, about 50 or so.
It's a good club. Elizabeth and I joined just after she got her license, and I knew some of the other guys. Russ has known my 14-year-old since she was about 4,
Hmm.
But yeah, it's on the 2nd of April. I can't remember I think it's 10 o'clock in the morning.
And somebody was asking, hey, do you want to get together so we can figure out how to use our radios? The Tualatin Valley Club has like a Elmer thing that occurs like a half hour before the club meeting starts.
Yeah.
That you can bring in your radio and the alleged experts will be there to show you anything you want to see and answer any questions you have. So it's a real good thing. And most clubs have that too. I mean,
Yeah,
that's,
we do too.
that's where you really find out something. So all you guys who get a license, join a club and that's how you get all your answers. You know, all your questions answered.
Yeah, the Valley Club in Eugene, we do that also.
Scott, do you have the information there about the address, the location of the Oddfart testing session? It's up in Hillsborough, at I think Hillsborough Baptist Church, I think. But
Right, the Hillsborough Baptist Church, and actually, you can just by going to the ARL site and say, show me the ham test closest to me, it'll come up.
Yeah. All right. Well, break is over. Everybody ready to go again?
Yep.
Okay. We are cruising right along, everybody. If you have any questions, now's a good time to ask. Okay, here we go. HF operation, which is very similar to VHF operation, except that on VHF, most of you will be using repeaters. HF is different from repeaters. You use certain terminology you never use on a repeater. So if you're operating on VHF, on a repeater, you never use CQ. CQ means I'm looking for someone to talk to. If you're on VHF on a repeater, for instance, the assumption is that you're on a repeater frequency and you never assume that there's not a repeater there that's going to answer. So you basically just throw out your call sign. If you're on 146.52, what do we call that again, everybody? What's that frequency called?
Universal.
That's the
National
national calling frequency.
National simplex calling frequency. Because it's simplex, there's no repeater there. We do use CQ on that frequency. You can call CQ, calling CQ on 14652 N7JI. Now, I might also say November 7 Juliet India. That would be called phonetics. The reason I use phonetics is because they eliminate some of the ambiguity of letters. Because CZ, CZ, G, and D all sound the same in bad conditions. Yes.
That was another one that I was going to ask you about. The CQ, if you were going to CQ, do CQ, how would you do it? How would you send it out?
Just send CQ. So you just say CQ, CQ. This is N7JI calling CQ.
Okay, so 2 CQs, doesn't matter.
Everybody's different. Some people some people will do a 3x3. Some people just do it once. Some people do it. I've heard some people do it like 25 times.
Oh, Lord.
Really quite annoying, but hey, you know, it's legal. So,
but the important thing is that you start the transmission with CQ.
If you're trying to find somebody on a frequency where you don't know if there's anyone there, then yes. So,
what about just putting out your call sign and saying listening?
You can do that, but you typically wouldn't do that if it's not on a repeater. If it's on a repeater, you just say N7JI listening, because the assumption is that there's a repeater there. If it's on a frequency where there's no repeater, you know, and you say, I'm just looking for somebody to talk to. CQ, CQ, CQ. This is N7JI. Calling CQ and standing by, or calling CQ and listening for a call.
I have a theory of why that one person does so many CQs.
Yeah.
Say you're on scan mode and they do enough CQs to pick you up.
Yeah. Well, the risk there, of course, is that if you do it for too long, people will get tired of waiting. The other risk, of course, is that you pick up too many people who are replying. And then you have and then you have to sift through them. This is actually true of contest stations, which we'll get to. So CQ means I'm calling anybody. When you're choosing a frequency to operate on, the first thing you do is make sure you're allowed to be there, right? So if I am on, let's say I have a technician class license, I pull up my frequency spectrum chart and I say, oh, I want to operate on 18.110. I look here and I say, okay, that band is for extra, advanced, and general. There, I don't, as a technician class operator, I don't have any privileges there. I can't be there. So first thing you do, make sure you're allowed to be there. The second thing you do, once you verify that you're allowed to transmit there, is that you make sure and listen to make sure there's nobody there. Now, the next thing you do is you ask, is the frequency in use? Okay, so why would you want to ask if the frequency is in use? How can it be in use if you don't hear anything?
Or in between statements.
Yeah, or let's say that there's A, B, and C. Propagation is a weird thing. So it might be that stations B and C are talking back and forth to each other, right? They're in the middle of a deep conversation. And station C is presently talking. And the propagation is such, remember, propagation is what radio waves go from place to place. There's a path that exists from A to B, but B isn't talking. And there is presently, because of atmospheric conditions, no path between A and C. And C is busy chatting away, and B is busy listening to them. And now you just said, is the frequency in use? Well, what will probably happen is that B will say, yes, frequency is in use. Even though you couldn't hear anybody there, you still had to ask, because technically the frequency is in use. And if you start transmitting, you're going to be interfering with the conversation. That's why you would ask.
Hey, Scott.
Yep.
One of the things is I was just doing the practice tests and whatnot somewhere along the way. It said just as a kind of a reminder for the CQ, if you think about it as SEEKYOU, seek you, like I am seeking you.
Yep.
So it's just something for people to remember.
Yep. And I think that's probably honestly where it came from. Now on Morse code, it also has a beautiful rhythm to it. So, you know, remember, because there was Morse code long before there was voice. Okay. Let's see. How should you respond to a station calling CQ? Russ, are you still here?
You bet.
Frank, are you still here?
Yes, still here.
All right. CQ, CQ, CQ. N7JI calling CQ and standing by. Who's going to answer me today?
Kilo Bravo 7, November Juliet Victor.
Kilo Bravo 7, November Juliet Victor. This is N7JI. Good afternoon. My name is Scott. Over.
Roger, Scott. Good to hear you. Name here is Frank, Foxtrot Romeo Alpha, November Kilo. I'm in Salem, Oregon.
We didn't turn it back to me yet. Frank, you got to turn it back to me, Frank.
I thought Russ was coming back in. Yeah.
Nope.
This is KB7NJV. Back to you, Scott.
All right. Thank you. KB7NJV. Thanks, Frank. And good that you're in Salem. My name is, again, Scott, Sierra, Charlie, Oscar, Tango, Tango. And I'm down in Eugene. And I thought I heard another station calling. So I'm going to cut it a little short and say 7-3, good luck. KB7NJV. This is N7JI. Over.
N7QR.
November 7, Quebec Romeo, N7QR. Good afternoon. This is Scott, Sierra, Charlie, Oscar, Tango, Tango in Eugene. Over.
Very good, Scott. N7JI, N7QR. Handle here is Russ, Radio Union, Sierra, Sierra RSS in Portland, Oregon. You're coming in full quieting, perfect signal, and weather here is clear. N7JI, N7QR. Over.
All right, N7QR, this is N7JI. Thank you, Russ. You're a solid 5 and 9 here in Eugene. And I thought I heard some other stations calling, so I'll say 7-3 and good luck to you. Have a wonderful afternoon. Over.
Very good. We'll catch you later. Thanks for the QSO and see you further down the log at N7JI and N7QR clear.
And this is N7JI. I wonder if there are any other stations calling. calling CQ and listening. Okay, so I didn't hear anyone, but that's basically how the whole flow goes. And the more you do it, the better you get at it. Take lots of notes. I always have a piece of scratch paper. Notice I have my scratch paper that everyone's looking at.
You have to log each one of those?
You do not have to log each one of them, but a lot of people log everything. I personally log everything because then once my log is complete, I will go and I will upload my log to this. Oops, wrong thing. Stop there. I will upload my log to LOTW, and LOTW is run by the ARRL, and it's basically a double-blinded call sign contact server where you can basically upload all your logs, and if somebody verifies that you made contact with them, then it will list as a QSL, which means that it's confirmed. Once it's confirmed, then you actually end up with a whole bunch of records in the database, and you can actually use them for awards, such as worked all states. So here's like my worked all states. Notice 160 meters is what I'm presently working on right now. As of November, I was at 4 states. Now I'm at 41. That's a very challenging band to work, which is why I put up that big antenna in my tree, and hopefully it's still working. 6 meters. 6 meters is another tough one because it requires meteor scatter or sporadic E, that weird mode of operating. It's in the VHF band. And as you can see, I still have a lot of holes on that band all over the country. So
Scott?
That's why I log everything. Yes.
Yeah, when we were exchanging the contacts there, I wasn't sure if you were pretending it was VHF or if it was HF, but I didn't do it, and I don't know if you and Russ did, but customarily included in the exchange, besides name and location, would be the signal report, of course.
Right. And you could on FM, on the repeater, you could sometimes say full quieting, which means you're basically there's no noise behind you. There's also something called an RST, which is a readability signal and tone. You may have noticed I gave Russ a 5x9. And so that was a perfect signal report, perfectly readable, perfectly audible. So RST goes from, that's readability, signal, and tone. This is 1 to 5, this is 1 to 9, and this is 1 to 9. So on Morse code, you would do the whole thing. On voice, you would just do R and S. So 5.9 is a perfect report. You could also be like a 3x3, which means that conditions are rough and you're not very loud. On Morse code, you'd be a 5.99. That's a perfect report. You could be a 3.39, which would be that, conditions are rough and you're barely being heard. I've gotten as low as a 1.19 before. So, but that still means they can hear you, and I still got a contact out of it.
So Scott,
yeah,
I've read that computers can be used in logging.
Yep.
Is that a program that you connect to your radio and it does the work automatically?
Well, I mean, when you say automatically, you still have to enter the call sign and stuff. But yeah, I log a lot of my contacts, especially during contests when things are coming in rapid fire. I have my computer connected to the radio, and it's recording the band and the mode and the exact frequency that the contact is being made on, as well as the data that I've entered. So if somebody in this, let's say this particular contest that happens once a week, well, it's actually four times for an hour on every Wednesday of the week. It's called the CW Ops CW test, or CWT. And the signal, the exchange that you give is simply name and member number, or name and the state you're in if you're not a member. So I would send people Scott 2348. And so like a sample reply that I would get would be Jim 885. So my log would contain like N0TA Jim 885, and then all the other information like the date, 3/24/2022, and the time, which was like 03:25 universal time, frequency 7.042068 megahertz. So all of this stuff would be entered automatically and pulled from the radio, which makes it a lot easier to log. The other cool thing is that that software, once you're done with that particular operation, you can basically then generate a file which you can upload directly into the logbook server for other people to match. So it makes it very convenient. You can also generate something called a Cabrillo file, which is a contest entry file if you happen to be competitive like I am and want to try to win the thing, or at least put in a contest entry.
What is winning a contest?
Well, it depends. Some people's interpretation of winning means that you made 10 contacts during the thing. For some people, winning means that you had the highest cumulative score in the entire world. So, and typically the most you'll ever get out of it is a nice plaque. More often than not, you'll get a certificate. And we call that, we basically call going for QSL cards and certificates, that's the act of paper chasing. And it's basically a way to improve your skills, build up the number of contacts you make, build up the number of states you've talked to, the number of different countries you've talked to, and so on and so forth, and have fun at the same time, and improve your abilities, improve your skills. Okay, let's see. When making on-the-air test transmissions, we're on page 70, by the way. When making on-the-air test transmissions, you have to identify this transmission. There's no such thing as a test transmission that doesn't have a call sign identified with it. A Q signal, there's a couple of Q signals that you have to know. You are allowed to do some Morse code. If you look at the frequency spectrum chart, you'll see that even a technician class operator can operate Morse code on any VHF and UHF band, and on the 40, 80, and 15 and 10 meter bands. So my son, who has a technician class license, also went through a Morse code training class about a year ago, and he has basically actually operated on Morse code in the station with me. So QRM means I'm getting interfered with by another station. And QSY means let's change frequencies, or we're changing frequency. Band plan. Okay, so what we're going to do is very conveniently, and now that we've started talking about this, we're going to look at this thing that says CW. Everyone see the CW? That's the red sections of every band. Actually, CW by law is allowed anywhere on any band, unless there's a specific law that says that you're not allowed to. To my knowledge, there's only one part of one band that doesn't even allow it, and it's not even shown on this chart. It's on the 1.25 meter band, and it is from 219 to 220. It doesn't even show up here. So, and that's because hardly anybody ever uses it. Okay, so the way that this works, here's 219 to 220. This band used to be from 220 to 225, and it was always kind of an oddball band. Well, UPS said about 20 years ago or so, hey, you know, we've got this package tracking system that we want to use VHF on. And so they basically agreed with the FCC that they would use 220 to 222 and give us 219 to 220. But because of the stuff that's already there, 219 to 220 is specifically only for message and data forwarding service only. It's a very strange little band, and you're not allowed to do Morse code there. You're only allowed to do message and data forwarding systems. It's kind of a weird thing. So it doesn't even really make it on this chart because very, very, very few people use it. But you notice that on this band, we have this red area. On this band, we have this red area. On this band, we have this red area. Basically, the fact that those are those red areas, and in particular, this one and this one, it's actually part of the FCC rules that you can only use Morse code on those little sections of the bands. But Morse code is allowed to be used virtually everywhere else. So, but the fact that these band plans are set up, notice that we have up on, let's say, the 900 megahertz band, SSB and weak signal, that's the light green. We also have FM repeater in the same area, and digital is the yellow stripe, and FM simplex. And we also have all this light blue stuff, that's amateur fast scan TV. The FCC, for the most part, does not tell us how we can use our frequencies, and we really don't want them to. So what we do is we create something called a band plan, which basically allows us to keep the peace on our frequencies by saying that it's not a rule, but by agreement, we're not going to use certain frequencies for anything other than this. And we have something called a frequency coordinator that is responsible for setting those up in every region. So in Oregon, we have the Oregon Regional Relay Council, or ORRC. That is a group of people that is selected by hams who are eligible to have repeaters or have repeaters. And they say, okay, we're electing you. You are now the unlucky person who's going to figure out what happens in case there's a dispute. So they set up the band plans and they to figure out how it all gets separated out. So if I look up ORRs, yeah, go ahead.
Do all those color sections mean by a peaceful agreement?
Yep.
Only that business is done in those colors. Don't try
Correct.
to do other things in those colors.
Correct. So
And
here's
so
like,
the CW dark red is the same pattern. Only CW by agreement should be
actually,
happening. in those patterns.
unless it's specifically in the FCC rules, and there are on 2 meters and 6 meters, it's actually specifically in the rules that you can only use Morse code there. With every other exception, without exception, everything else is just by agreement. So this is, for instance, the 2 meter band plan in the state of Oregon. And notice we have by agreement 144.01 to 05 is EME, which is Morse code for moon bounce. And then we have 144.06 to 144.1, which is Morse code, CW, weak signal. And that, notice that says uncoordinated CARRL band plan. So that actually says, okay, we're not even going to bother talking about that stuff. The ARRL has decided nationwide. But then there's this other one, 144.39. Notice that says single use national designation. That's packet radio for APRS. That's nationwide. But then we have these other areas that say repeater outputs, repeater inputs, simplex repeater, repeater inputs. Those are all allocated and decided on by the Oregon Region Relay Council. And then inside of that, once those are agreed on, notice these are a list of all the coordinations. So if you want to put up a repeater, you'd basically apply and say, I would like a repeater pair, a pair of frequencies that I can use, and they'll figure out what frequencies would not interfere with anybody else and are thus available, and assign them to you. And then once that's there, you can put up a repeater. Notice there are a lot of repeaters in Oregon. There's a lot of hilltops in Oregon.
Who brings the dispute to the coordinator? The FCC or do people call the coordinator?
Oh yeah, you basically go to the coordinator. if you want a repeater, you talk to the coordinator. Because remember, the FCC rules, by virtue of getting a license, what does that allow us to do? It says, we trust you, go put up a station. If you want to
Yeah,
put up a
those are
station,
they're all volunteers, those guys.
yeah. Again, those are, volunteers who have elected to say, and they've been voted in to say, okay, well, we're going to be the ones who settle all the disputes and hand out frequencies.
So technicians could set up a repeater?
Yep.
And is there an advantage to setting one up other than just wanting to do service?
Nope, not really. Unless you want to, have something, you could actually set up a closed repeater system. Very few people do, but you could set it up so that you need like a special code to use it and hand it out to only a certain number of people. Most people don't do that. Most people, if they're going to go to the effort of putting up a repeater, will open it to everyone. But there's no requirement to do that. Okay, how do you, let's see. We're talking about public service and emergency communications now. Oh, actually, before we get there, who owns a frequency? Unless it's been assigned by a repeater coordinator or something. So let's say two stations show up on the same frequency at the same time. Who owns it?
Nobody?
Nobody. That's right. So it's up to you guys to figure out who gets what frequency when. Like somebody might say, hey, we have a net here, a net we're going to talk about in a minute. It's met on the same exact frequency every day for the last 40 years, and we typically have 50 people checking in. Could you guys move for us so that we can run our net? The answer is probably sure. Okay. So we'll move a few kilohertz up or down the band and give you guys the space you need. So basically, we try to be neighborly and good to each other, because we don't want Big Brother deciding for us who gets to use what frequency. If you can keep the peace on your own, then you don't have to ask for help. Okay, public service and emergency communications. We have ARES and RACES. They are both they are both amateur radio for public service. One is ARES and one is RACES. ARES is the amateur radio emergency service. RACES is the radio amateur civil emergency service. The only difference there is that this has the word civil in it. So basically, ARES is a volunteer organization. RACES is a volunteer organization where people in both, they would register their equipment and their time to help out in case of emergencies. In the case of RACES, that addition of the letter C means civil, which means you actually, instead of registering with ARRL, you would register with your civil defense organization. So that could also be civil service. That could be the state. So your RACES could be like, it's similar to like Civil Air Patrol, except that once again, it's amateur radio. So basically, if it has that letter C in it, that would mean that it's for civil service, civil defense. So you'd register with a state regulatory agency. Both of them can provide communications during emergencies. Both of them are used for emergency management. Both of them are used for emergency situations. Both of them can carry emergency traffic. They can carry health and welfare traffic. In Eugene, actually all over Oregon, we have a hospital net where we have a lot of hospitals within the state, medical agencies within the state have a separate network where they all have a backbone of ham radio systems, and they can either communicate over simplex networks or over repeater systems. And in case of emergency, they can coordinate between each other and between the state and figure out what hospitals have extra space or what hospitals are functioning, what emergency rooms are available as kind of a backup to networks that might not be functioning in case of emergency. NCS is Net Control Station. So if one thinks about a network, we have a hub, that would be the NCS, but we have other stations at the ends of all these spokes. Coming off of the end of one of these spokes, for instance, we might actually have additional spokes because this person here might be in kind of a far-flung place, in which case that person could actually serve as like an alternate NCS or could run things called relays. Another station here, let's put them way out here, might be able to access people who are out here. Whereas the central net control station might not be able to just because of geography. There might not be a repeater station up and running. So this would be something like a simplex net. At which point net control station is the person in charge of traffic moving back and forth between all those people. So picture every one of those dots as a person with a radio. So in case of an emergency, information has to travel back and forth. So let's say that there is traffic that's initiated here, where I drew that black looking squiggly thing. And the end target of that station, of that traffic, is somebody way down here on the other end. So clearly this traffic would have to go through here, through net control, through here to this station. So it would be the job of net control, as well as this station here and this station here, to make sure that the traffic, which is information, a message, a formal message, got transferred from point to point. This is exactly how the internet works, except that it's all done automatically, right? If the internet isn't there, we actually have people on the air. They can actually read messages to each other. They can also use something called WinLink, for instance, which is like a semi-automated digital communication system for moving traffic from place to place in a digital format. So computer to computer. But in any instance, what happens with the net control station is that the net control station might say, like station 1 up here, the green hub might say, okay, well, I got information from there. And the net control station might say, okay, does anybody have any traffic for the net? And station 1 would say, yes, I have traffic, and it's destined for this particular target. So that traffic, which is the information, which says originating from this station in this location, going through the net with a target of down here, here's the message. And so you basically give the message exactly as it was sent, and then you'd include something called a check, which is the number of words or word equivalents in the message to make sure that there were no errors, something like a checksum, like we were talking about with digital. Then once it's handled, the net control station would say, okay, you're released, I've got the message. The net control station would say, okay, station number 2 down here, I have traffic for you from here that was received at certain time. Are you ready to receive the message? And the message would get transferred down to this station. Once received, that station would then say, okay, I've got it. And then on another frequency would go over to this station and say, okay, hey, station at the end of the chain, I've got a message for you that originated from blah, 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 and the message gets passed. So the net control station is very important because the net control station determines who does what when. So the net control station, it's good for people to practice being net control because you're essentially the traffic cop. You decide how things are going to run. Now, if there is an emergency, let's say that somebody has to get the attention of net control, you would say priority or emergency. Sometimes you would use the word break, depending on the net you're on. And that would get the attention of net control. Okay, traffic is formal messages handled and passed by net stations. Good traffic handling is making sure that you don't lose any information. We use something called a check or checksum, again, to make sure that no words got lost. One of the good uses of the phonetic spelling is, for instance, okay, if somebody told me somebody's name was Alex, how would I spell Alex? Well, it could be A-L-E-X or apparently A-L-I-X. I actually know another person named Alex. So if it was A-L-E-X, I would say Alpha Lima Echo X-ray. I would spell out A-L-E-X using phonetics. If it was A-L-I-X, I would do Alpha Lima India X-ray, so that there was no ambiguity in the spelling. So that's why you would want to sometimes, if it's a name or a word that isn't common, spell it out using phonetics. Okay, the preamble of a formal message is the header, indicating where it came from and how to track it and where it's going to go. So basically all the tracking information. The check, again, is the number of words or equivalents that are in that message. Sort of like, again, that checksum. And okay, so now, when do the FCC rules not apply to the operation of an amateur station? And the answer is they always apply, but when are you ever allowed to transmit? Let's say that there's this net going on, and this net happens to be on military frequencies, right? Because the military can run nets also. Could you ever break into a military net? What do you think?
In an emergency.
In an absolute emergency, that's right. So the answer is, are you ever allowed to operate outside the frequency privileges of your operator of your license class? Well, the answer is, if it's an emergency involving the immediate safety, you're going to hear this over and over, immediate safety of human life or protection of property. We have a fire, the dam is going to break, we're going to have people who are flooded out, the waters are rising. Those are emergency measures. And it's okay at that point, if you have a technician class license, to get anybody's attention on the ham bands, or to be honest, anybody's attention anywhere, because you basically have an emergency. Now, the question is, what are you going to have to do to explain yourself at some point? And the answer is, you're probably going to have to explain yourself at some point. Why did you do what you did? Why did you break into this military net? And the answer is, because somebody was going to die, and the FCC will probably say when they do their inquiry, okay, you actually did it right, everybody's good. So basically, unless there's no other way, only if there's no other way to get the word out, should you do this, but you're certainly allowed to. Okay, we're into satellites. We are allowed to put up our own satellites. If you are at Portland State University, something called PSAS actually just put up a couple of CubeSats, which are now floating around in space, 200 something miles up. It's a 4x4x4 inch box that is floating around in space, sending signals up and down. So
yeah, 1U, right?
Yep, a 1U, which is 4x4x4 inches roughly. That's a very tiny little CubeSat, but it's still expensive to build and it's still expensive to put up there. But it can be done. Who's allowed to make contact with the International Space Station? It's on 2 meters. What license class do you have to operate on 2 meters? You need a technician or higher. Now, the question is, why does it say a technician or higher? There are actually licensees who don't have a technician class license. There are actually 5 different licenses out there, of which you can only get 3 now. There's a novice, a technician, a general, advanced, and an extra, going up in license class. The novice hasn't been given since about the early 1990s, but there are still people out there with a novice class license. In order to get a novice class license, you had to do Morse code and take a very simple exam. The novice class operator has no privileges except for the 1.25 meter band and the 23 centimeter band. Novice is a very weird dinosaur of a dinosaur of a license class right now. But if you have one, we actually had somebody back in October who took this class who had a novice license from 1986 and had never upgraded. So she actually went from novice to technician and then technician to general. Then there's this other license class called advanced, which used to be 13 words a minute of code and a hard written exam. You can't get one of those either, but they still exist. So she actually upgraded from novice to technician to general, then to extra. She actually quite likely will be giving you some of your exams tomorrow. This happened over a period of about 2 months. She retired and had some time finally. Okay, mode UV. UV is UHF up. And we're going to erase that. And VHF down. And again, this is mode UV. Typically, this is 440 megahertz up and 146 megahertz down. 440 megahertz would be the 70 centimeter band, which is definitely UHF. And this would be the 2 meter band coming down. So that again is mode UV. Now you can also operate mode UU or VV or VU. Modes of operation of satellites, they can be single sideband, which would use a linear transponder. They can also be Morse code or data. You can actually have floating around up there, like they do on the International Space Station, a packet bulletin board system. At least they did at one point. That would be a packet BBS, which means you could upload using packet radio a message that was addressed to somebody else and store it up here in the packet bulletin board. And then when this other station connected to it, they could say, send me my email or send me my packet message. And it would be stored up there and then sent to you once you collected it. Basically a mailbox. You can also, of course, use FM. FM is the most common mode for satellite communications. Because a satellite has, like, if you think about it, most of them have like a repeater on board. They have an uplink and a downlink frequency. They also transmit something called a beacon, saying, hey, the satellite is overhead, come and get me. Well, if you are transmitting on an uplink and you're transmitting with too much power, the satellite downlink, your signal will be too loud and other people won't be able to get in and other people won't be able to get heard. So you try to make your signal that's coming out about the same sound audio-wise as the beacon. Low Earth orbit. A low Earth orbit satellite is something that's about 200 miles up. And let's say 220 miles up. And Abhijit, do you know what the altitude is of the CubeSat by chance? Don't hear anything. Okay. Well, a geosynchronous orbit is about 22,000 miles up. So the lower Earth orbit satellites tend to be going around at a very high rate of speed compared to the ground, whereas a geosynchronous orbit tends to stay directly over one particular point. A satellite beacon contains information about the satellite, as well as, for instance, things like battery voltage and whether or not a particular radio is up and running, what the temperature is on board, health and status of the satellite, basically. And because you are not actually transmitting to get that beacon information, you do not even need a license to receive a satellite beacon information. So as the satellite is passing overhead, it could be just as simple as saying beep, 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 beep. If you have a receiver, you can listen to the beep, beep, beep. This was the first thing that happened back in 1957, I believe, with something called Sputnik. Basically, Sputnik was put up in space and it just floated around and went beep, 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 beep. But it was floating around in space. Now, about 25 years ago, there was a celebration of Sputnik, and they put up something that was like a new version of Sputnik. And that was, as it was traveling around, that's all it did. It just went beep, 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 beep in honor of the original Sputnik. Okay, let's see, what satellite tracking programs. Okay, so because a satellite, what we're going to do is take a look at AMSAT satellite tracking. So we're going to look at ISS for CN84 passing overhead of me, calculate position, and here are the next passes, and now we're going to show them on the map. Okay, so this is what the International Space Station is going to be doing directly overhead. So it doesn't go directly overhead right now in Oregon, but let's take a look at another satellite. Let's pick a different one. And notice there are a lot of amateur satellites to choose from. And we're going to pick, let's see if ORSAT is up there. Nope, it's not listed on this one. But let's pick AO91. This is a classic old school satellite. And what we'll see is that it has a different orbit. It's a more angular, a more polar orbit. And it is at a different place in the sky right now. So you can actually use AO91 to bounce signals up and down. You have to look up and see what AO91 is carrying on board. But basically, what does a satellite tracking program do then? It gives you the time and azimuth and start, elevation, etc. of the pass, essentially the duration of the pass, saying how high this is. Notice the elevation, 64 degrees. That's a high altitude pass. It starts at 0700. Notice the time is in universal time. What's nice about that is that universal time is the same all over the world. It used to be known as Greenwich Mean Time. So this is a kind of a way of having everybody on the same clock all over the world. The time when the satellite disappears from view, the azimuth, this is going to be close to north, that it shows up the loss of signal. So it's going to be a little bit west of south when it disappears. And so anyway, so maximum maps showing the real-time position, all the data as far as passes go, and the apparent frequency of the satellite transmission, including a Doppler shift. So Doppler is something that you will hear when a fire truck goes by, and it goes because the waves get compressed, so the frequency goes up as the thing is moving toward you. As the thing is moving away, the waves get stretched out. And if we don't know what the difference is, if this is a fire truck coming toward you, the waves get compressed. As the fire truck goes away, the waves get stretched out. Well, if they arrive in a more compressed format, that's a higher pitch. If they arrive in a less compressed format, that's a lower pitch. Doppler shift changes the apparent frequency that you hear. Well, in radio, if we replace this with a satellite flying around at very high rates of speed, what we will see is that the satellite, as it's coming closer to you, will actually have radio waves that are compressed. You'll actually have shorter distance between them. As it goes away, you'll have more stretching of the waves. And what will happen is you will actually get a higher frequency and a lower frequency. Now, unlike sound, how fast does light travel?
300 million meters a second.
300 million meters a second, which is about 186,000 miles per second. And a satellite will be moving at, let's say, 7 miles per second, which is pretty darn fast, right? but it's still not that big compared to 186,000 miles per second, but it is enough to cause a noticeable Doppler shift. So if you are trying to operate through a satellite, let's say I'm using the International Space Station, which has a frequency of 437.800 megahertz. That's the nominal uplink frequency. As it's getting close to you, you might have to be at 437.790. Then when it's here, you would switch to 437.795, then 437.800, and then it's going away, 437.805 and 437.810. And I have actually done this, and it is actually a very noticeable thing. So Doppler shift is a very real thing, even with radio waves, and it actually changes the colors of light a little bit and all kinds of cool stuff like that. The elements which a satellite tracking program such as this uses in order to plot the positions and all this good information about satellites, these are known as the Keplerian elements, named after Johannes Kepler, who did a lot of stuff with planetary motion and planetary physics.
Does that site allow you to try to find a satellite that's going over you right now?
That is a good question. I've never looked for that. You would actually have to plot a whole bunch of them and see what's overhead. I don't know if it goes backwards. I'm sure there are different packages, software packages that wouldn't be a website, for instance, or maybe even some websites that you could say, show me the satellites show me the ham satellites that are going overhead, and it would allow you to do that. But I haven't seen it. Spin fading of satellite signals. Satellites, in order to keep their position in space, are typically tumbling. They're spinning. And if a satellite, let's say that looks like this, has an antenna system that looks like this, as the satellite is rotating in space, sometimes the antenna will be pointed like that. Sometimes the antenna will be pointed like this. It will be in different orientations, and you will actually have fading when an antenna, for instance, becomes eclipsed. If I'm looking at the satellite, the antenna becomes eclipsed by the satellite temporarily. That's known as spin fading, as the satellite rotates out of view. Okay, operating activities. I believe we're now on page 77. Okay, contesting. A contest is an opportunity to make as many contacts in a short period of time, or sometimes a long period of time, as possible, and compete with other people and compete with yourself. So, for instance, this is kind of called radio sport. This week alone, these are all the contests that are occurring around the world. Notice every one of those bars, and oh, cool. CQWPX is this weekend. I didn't even realize that. So some of them, notice, are as short as an hour or two. This big one in the middle, that's 48 hours long. That's a worldwide 48-hour long contest. And you can see that here are the rules. Those are the frequency bands that it's on, 160 through 10 meters, worldwide, single sideband. And you can operate, if you're a single operator, you're allowed to sit in the chair for as much as 36 hours if you want, if your butt can take it. And 6 points per 6 points per contact on the lower bands, 3 points per contact on the higher bands. And if you're in North America, 4 points on the lower bands in the same country, and so on and so forth. So then there's official rules, places to upload your logs. So basically this gives you all the information as to how to operate and compete. So you can choose the class that you're operating in. You can choose the power level that you want to use. You can choose the size of the antennas you want to use, how much time you want to sit your butt in the seat, and it's a good chance to get a lot of practice. It's a good chance to become a better operator. Now, the other thing is that this is not typically a chit chat kind of thing. You know, I'll get on, for instance, I'll talk with somebody who's a friend of mine on a repeater and we'll have a 20-minute long conversation. In something like this, which is called a contest, you would typically send only the information needed to log the contact and then move on. Because your goal is to make as many contacts in as short a time as possible. There's time for the chit chat later. Now, sometimes we indicate where we are on the planet by using something called a grid locator. And the grid locator is, I believe, something that I included in your packets as well. Let's see, radio. Here's the packet and grid locator, grid square map. Okay, there we go. So this is a grid square map of the United States. The whole world is actually broken up from AA to XX. Those are the 20-degree in longitude by 10-degree latitude squares, which are actually pieces of a sphere. So they're not really squares, but they're called grid squares. Each one of those is then broken up into a 10 by 10 section or 10 by 10 grid. So you have 0, 0 up to 99. Within each of those is then broken up into 24 by 24. So you could get even more detailed. The reason that we do this is because notice that some states, some countries are really big. So let's say that I'm in Oregon and I'm marking this as CN84. And let's see, who here lives on the East Coast, somewhere east of the Mississippi? Jim, where are you?
South Carolina,
Okay, where in South Carolina?
near Spartanburg.
So that would probably, that's upstate. So you're probably either EM84 or EM94. Well, South Carolina, as you'll see, comprises a whole bunch of different grid squares. So if I am pointed and somebody tells me that they're in grid square EM94, that tells me where to point my antenna. Now, that's not as big of a deal because South Carolina looks kind of small from Oregon. But let's say I'm talking to somebody in Idaho. Well, from Oregon in CN84, Idaho goes all the way from up here in northern Idaho, which would be DN18, all the way down here to DN12, which if I look at my azimuth, that would be northeast all the way to a little bit south of east. So just knowing somebody is in Idaho doesn't really tell me anything about which way to point my antenna. If I have something that's a very narrow bandwidth antenna. So what it allows us to do is identify locations like Montana. Montana's actually got what, 24, 25, 26 grid squares. Texas has even more. If you're in, let's say you're in New Mexico and you're pointed at Texas, are you pointed north or are you pointed south? So it really helps to know. It breaks things up a little bit more. And that's known as the grid locator map.
Scott, I have a question related to like something that I picked up in one of the sci-fi movies.
Yep.
It's like when someone says that, okay, send a narrow beam or send a wide beam, is it like wide beam relates to a broadcast and narrow beam is like you're pointing to someone?
Well, when you say a broadcast, I mean, yes. I mean, in that regard, yes. And if you look at the gain of an antenna, so let's take a look at an antenna that has a lot of gain. Let's make a dish. That typically is going to have a fairly narrow beam width of the signal coming out of it.
Mm-hmm.
Right? So, and actually, if we were to plot the beam, the pattern of this antenna, we would actually see that it looks something like this, with a little bit going back. And so here's the peak right here. And we also have a definition to define the beam width of this antenna pattern.
Mm-hmm.
Typically, this is known as the half power point. How many dB would that be, everybody? How many dB down from the peak?
3.
3 dB?
That would be 3 dB. That's actually known as the 3 dB beam width of an antenna. That's how we usually define the beam width of an antenna in degrees. Looking from here. That would be our beam width. So There you go.
You have
There's
the dish itself on that
what?
diagram?
Oh, yeah.
On the red diagram, just overlay the dish.
Yeah, the
Thank you.
dish would be right there pointing that way. So the higher the gain, typically the narrower the beam width. So if you're talking about an antenna that looks like this, which has a whole bunch of directors on it, that's going to typically have a lot more gain than something that looks like that with only 3 elements.
Okay.
So your pattern is going to be much more pronounced versus something that looks like this. And so if I were to, again, draw that 3 dB beam width, I'd see that it was like there versus that.
Yeah, thanks.
Okay. All right, let's see. Which of the following methods is used to locate sources of noise interference or jamming? That would be direction finding. Typically what we do is we take an antenna here and we take an antenna here and we take an antenna here. You can do it with one. It's a lot easier to do it with multiple people where you basically then say, okay, well, it's somewhere in this area and it's somewhere in this area and it's somewhere in this area. Well, okay, here's my intersection point. We're looking somewhere in here. That's how the FCC does triangulation on interfering stations. We also do it for fun. This is actually called fox hunting. Allows us to practice finding the hidden transmitter. Which of the following is useful for a hidden transmitter hunt? That would be a directional antenna, just like this one or this one or this one. Internet Radio Linking Project, or IRLP. That is a method of combining radio and the internet using something called VoIP, which is Voice over Internet Protocol. Essentially, you take a radio and you basically will create a digital bit stream of your voice and send that in a digital format over the internet, and it pops up somewhere else on the internet, which can then be listened to directly or put through another repeater in an analog format. Echolink. Echolink is another method of doing this. So basically I have my phone or my computer, which is on the internet, and it connects over VoIP to a repeater, which is on it, and it transmits my signal. So actually I can operate on a repeater using my cell phone. And I have actually used this from all over North America to check into local nets on my on the Valley Radio Club's repeater. We have periodic nets, and if I'm, let's say, in North Carolina, which I was, I can just basically log in from North Carolina and operate over the repeater as though I were somewhere in Oregon. And that's known as Echolink. In order to use Echolink, you actually have to register as a ham radio operator. So you have to provide your name, your call sign, and your proof of your license. So you actually have to send them a license so they can register you. How do you obtain a list of active nodes that use voice over internet protocol? You can subscribe to an online service. You can use a repeater directory or go find an online list that's maintained by the frequency coordinator. Basically, if there's a connection between the internet and radio, somebody will have it. Somebody will have a listing and you'll be able to find it. How is access to some IRLP, Internet Radio Linking Protocol nodes made? And we use something that looks like this. That looks like the old school touch tone pad, does it not? And in fact, every radio, if you key up the push to talk button and then start hitting buttons, you will actually send touch tones, which are known as DTMF, or dual tone multi-frequency. And the proper sequence of tones that you press, the proper sequence of keys, can actually bring up a link between a repeater and the internet. Those nodes are known as gateways.
I know.
As what?
Those nodes are known as gateways. It's a gateway to the internet.
Too much information.
Okay. Everybody doing okay? Because we're into rules and regs now. This is the driest part of the whole thing, but we're almost done. Would you rather just blast through it or should we take a short break?
Short break.
Short break. Okay, I'll be back in a couple of minutes.
IRLP is how I used to talk to my daughter out in Washington, DC.
There you go. And actually, that's how I connect to my local club here for all of our nets. Although that's Echolink, but Echolink uses IRLP.
And
It's a
so
form
if
of
there is a gateway to the internet, to what degree is ham radio used for misinformation?
That's a good question. I mean, when you say misinformation, I mean, it's a communications tool. Anything can be used for misinformation. I don't think most people do.
That's what I wondered about.
It's not worth the effort. You know, it's really
the
just
nice
not
thing about CW. There's no misinformation on CW. People are super polite.
Yeah, I'm glad to hear that. That's, I was just wondering what the environment was like.
Actually, I hate to say this, but the Willamette Club has got a news group, and even on their news group, they said, in keeping with ham radio protocol, we don't allow any discussion of sex, religion, or politics. But I don't know if it is strictly speaking. There's a lot of people who talk about a lot of things on ham radio.
But somebody suggested that ham users are polite and they wouldn't spread misinformation, but that assumes that people spreading misinformation are not polite and don't realize that they're doing a bad thing. They're doing what they think is the right thing. And so how does that keep misinformation from spreading on the ham? They are polite.
There's always a 10% lunatic fringe in any portion of the population. So you do hear some things, but not a lot, I would say. Usually people avoid politics on ham radio. And in fact, that's a big issue now too, to tell you the truth. Ukraine at the moment is under radio silence. And there's a big issue of whether the contest this weekend, whether the hams should talk to Russians or not.
Yeah, and legally, there's no reason not to. And, by the FCC rules, it's supposed to cover, international goodwill. But if it's something that you don't feel comfortable doing, then you shouldn't do it. It really comes down to your conscience. Agreed, Russ?
Yeah.
Yeah, matter of fact, they're still debating whether the call sign for Crimea should be Russian or Ukrainian.
Oh, I know.
So I don't know. I mean, there's a lot of controversy. The biggest controversy though in ham is whether we should eliminate Morse code for licensing or not. But that's that's 20 years old already.
Right, that's a
They're still
non-issue.
debating it.
Yeah. That's a non-issue at this point.
I know, but there's a lot of people that would like to.
Actually, it's not a non-issue. Can I tell you why it's not a non-issue? Russ, you want to know why it's not a non-issue?
Yeah.
Because technically, if you get a CEPT license, and in some other countries, there is, like, I believe when I went to Uruguay, it's not a CEPT license. It's covered by the Inter-American Radio license. Inter-American Radio permit, conceivably, part of it actually says that to give you the full license equivalent there, you actually have to have proof of being able to copy 12 words a minute. So if somebody were to take a US amateur extra license and get a translation of it and operate it in another country, they could conceivably ask you to copy 12 words a minute because it's still written in there. And believe it or not, the Anchorage Amateur Radio Club will still give you a 12 word per minute exam if you want. So you can actually get certification of being able to copy if somebody were to ask.
Yeah, the ARL has a thing, you can get a proficiency award.
That's different. This is actually something that is a test element.
Oh,
that you can get. You can actually get certification.
Is that fast?
What, 12 words a minute?
Yes.
Not to me, it's not.
that's like the basic speed for just shooting the breeze.
Yeah, for enjoying. Well, I mean, 12 words a minute for me is really slow. I mean, really slow. I mean, I can in a burst, I can copy 45 or 50 words a minute.
So
Yeah,
it's
better
fast.
than me.
Dot, dot,
My
dot,
my
dot,
my
dot,
problem, I'm stuck in the copy every stinking letter, and I can only write it about 25 words a minute.
Well, see, I can't write. I don't even bother. I just do it all in my head.
Exactly.
Which
If
is
you're
why,
good.
but that's also why I've never applied for the code proficiency certificate. I don't know if you can actually type it legally because it says handwritten in the application. So I'm not sure if I'm allowed to, or if I have a little tape recorder and as I hear it, I just speak out the word that I copied and then translate it.
It's really a language. You have to really copy words to get up at that point. And I mean,
Yeah.
it's like English. None of you guys who are listening to us are listening to us letter by
every letter
You're
at a time.
actually, you're listening to us right now speak word at a time. And that's really where you have to go if you want to be a real good CW operator.
Yeah. All right, you guys ready to cover the last parts? These are the rules and regs. This is the dry stuff, but it's important to know. Okay, so the FCC, Federal Communications Commission, governs amateur radio in the United States. The FCC, we covered those 5 things. I'm not going to cover them here. Those 5 things that that makes up amateur radio in the United States. The reasons that we exist. And one of them, again, was international goodwill, and there's advancing skills and things like that. So take a look at those. Again, there are 5 of them listed in the FCC guidelines. And, I could actually pull them up while I'm talking. So the rules, the section of the FCC rules that govern amateur radio, you need to remember this. I can almost guarantee this will be on every test, is part 97. 97. That is the section of the FCC rulebook that governs amateur radio. A beacon station is a station that transmits communications for the purpose of observing propagation and related experimental activities. So a beacon is a one-way signal. Most signals that we use are two-way. It's designed for people to talk to each other. We do two-way communications. Beaconing is a one-way signal. A space station
purpose
again.
of what?
What?
It's a one-way signal to do what?
To see whether or not there's propagation between 2 points on the planet. Or to, for instance, let's say you put up a weather station. The beacon could say, well, temperature is 26 degrees. Temperature is 26 degrees. It's basically some kind of experimental purpose. Either
an experimental what?
Some kind of experimental purpose. Either you're doing an experiment and you need to get information across, or you just want somebody to see if they can hear a station that's transmitting from somewhere else. A space station, again, is anything that's 50 kilometers above the Earth's surface. So high altitude balloon, nope. Airplanes, nope. It would actually have to be 50 kilometers, which is about 31 miles up, which is about 160,000 feet. So that's where space begins. When are you allowed to willfully interfere with another station, even if they're really pissing you off? Never. Some people, this gets the better of them. And then they end up getting a fine from the FCC because they allowed they allowed it to get the better of them and they started interfering with other stations. So because you have an FCC license, you're governed by the same rules that radio and TV stations are governed by, which means you're not allowed to curse on the air. You're not allowed to do anything like that. You're not allowed to do anything that's indecent or obscene. A volunteer frequency coordinator coordinates all the channels, and amateur operators in a local or regional area whose stations are eligible to be repeater or auxiliary stations choose the frequency coordinator. So basically, frequency coordinator, the thankless job. Okay, the ITU is the International Telecommunications Union. It's a United States, it's a United Nations agency for information and telecommunications. That is the ITU. So every country that is a member of the UN is also subject to the rules of the International Telecommunications Union. Okay, so let's just take a look really quick at ARRL Part 97 text. Again, really dry, but important. And right here are basis and purpose. These right here. This is why we exist. And if you would like to see, it is subsection 97.1 of the FCC rulebook. And what I will do is I will put that, if you're really interested, out in the chat. And it's part 97.1.
What are we going to find there?
The reasons we exist.
Oh, with the 5 things?
Yep. Those are the 5 reasons that we exist. Okay. So the next section that we covers individual frequencies that we're allowed to transmit on. It's really important actually to understand the band plan and know what frequencies are the limits for each band. So 6 meters is 50 to 54 megahertz. 2 meters is 144 to 148. If you were to look at this thing that says 2 meters, this is the approximate wavelength of that band. It's not exact. In some cases, it is exact. In a lot of cases, it's not, especially down here on HF. 10 meters. What's 300 divided by 10, everyone?
30.
30. Clearly 30 is not anywhere between 28 and 29.7. So that is called the approximately 10 meter band. So we call it 10 meters for that reason. Let's see, if we were to say that we're on 146.52 megahertz, which again, what's the name of that frequency?
National calling.
National simplex calling frequency. You would see that it is on the 2 meter band. So why should you never transmit right at the edge of a band? If I were to draw this band, for instance, and here's a frequency band, and here's the bottom and the top, I have a signal that is right here. And if I know what my modulation sidebands look like, it looks like that. Would this be a legal or illegal signal?
Legal,
Illegal. Why is it illegal?
because we have some signal crossing our band.
That's right. There's a little bit of the signal that is no longer inside the lines. So that's why it's important to know. That's another reason we're taking this class. That's another reason we get licensed. We are assumed to understand that what our signal looks like determines where we can put it. So if we were to do lower sideband and the signal looked like this, only half of it, would we be legal or not?
No.
Yeah, our signal is completely inside the red lines.
Yeah.
If we were to switch to the upper sideband up here, whoops, our signal would now fall partially outside. And then we would not be legal. So what would be our remedy for this, assuming that this was the mode we wanted to operate on?
Move a little bit to the left.
That's right. We'd move our signal to the left and then our signal would fall right there. And then we'd be okay. And that is why you never set your frequency to exactly on the limit, because depending on what you're doing, if your radio is off by a little bit, even if you think you're in the band, if your radio's off a little bit, or your modulation sidebands, there's a little bit hanging out over here, or it over time changes by 1 kilohertz, all of a sudden you're not in band anymore. So that's why we don't go all the way to the edge. Okay, let's see, back to the weird frequency chart, which doesn't have 219 to 220 on it. We would find that that is used for fixed digital message forwarding systems only. That is the only place, that is the only mode we can use on 219 to 220, which again would fall somewhere to the left of this 222. Now let's take a look at the 10-meter band. Notice that you have this stripy thing, which says star, this blue stripy hatch thing. It says novice and technician voice. You are actually, with a technician license, allowed to operate on the 10-meter phone band, which is actually pretty cool. It's actually been very good of late for talking to people overseas. You are actually able to also use those bands. Notice this says CW, RIDI, and data. RIDI is teletype. You are actually allowed to use that section of the 10-meter band for digital communication. So if you want to practice playing around with digital with a technician license, you can do that. Up here on the 6-meter band, notice we have those little red stripes, 6 meters and 2 meters. Those are Morse code only by FCC law. If you are operating as a technician class operator down on the HF bands, and the limits on HF again are from 3 to 30 megahertz. If you are operating in one of these areas where you have a T or the star, that means you're allowed to operate there. You're allowed to operate with an output power of 200 watts, believe it or not, which is more power than I ever run. If you're operating, with a few exceptions, on these upper bands, anything 6 meters and shorter wavelengths, you're allowed to run 1,500 watts, unless there are specific rules where you live. In addition to that, you might also find that you hear other stations on a band where you think that you are allowed to be. They are possibly allowed to be there too, because they might actually be primary or secondary users. We're not always primary. On that 70 centimeter band, which is 420, that big swath from 420 to 450, right up there, the 70 centimeter band, we are actually secondary users to the US military. Notice this also says 420 to 430, not available along the Canadian corridor. So that basically means that other licensed services have priority. And if the military comes on and says, hey, we need to use 420 megahertz, we're not allowed to talk to them. And if they ask us to go away, we have to go away. Okay, license classes that are available from the FCC right now. They are the technician, the general, and the amateur extra. No, I don't know why it's called amateur extra, but that's what it's called. A license is good for 10 years. You do not have to get retested after 10 years. You can simply renew. When can you operate? As soon as the license shows up in the database. You don't even get a piece of paper anymore. They just put it in the database. And once you do a search for it in the ULS, which is the exact same thing that you looked, that you got your FRN in, you're allowed to operate if it's listed as active.
What's the Canadian corridor?
It's along the western part of the United States, and I believe it's about 1 degree of latitude.
Called line A.
Is it line A? Yeah, whatever line A is. I thought it was about 1 degree of latitude.
No, I think it goes the entire length of the Canadian.
Does it go the whole way?
Yeah, because I know I didn't, but somebody in my office got burned. If you wanted to go to Canada from Chicago, which direction would you go?
Oh, you go east.
Yeah, a lot of people don't realize that.
Yeah.
Sure
And
enough,
maybe a little
it's
from
only-
Detroit, you go a little south.
Yeah,
So
it's only 190 miles from Chicago to Windsor,
yeah, from Detroit, you go south.
which means that Motorola could not put up their commercial repeaters on the Sears Tower
Really?
in Chicago.
Too close to Canada. Okay.
Too close to Canada.
Yeah. Okay.
Question on the band plan,
Yeah.
on the section MFHF band plan,
Mhm.
it doesn't seem to tell me whether those are megahertz. The above section, everything is in megahertz, and down there, it just doesn't use that term
On the band plan chart,
on the end of the band plan. So like 10 meter.
they're
it
all
goes
megahertz.
28 to 29.70 watts.
Well, you know that HF is 3 to 30 megahertz, right? Because that was one of those things to remember, that VHF is 330 to 300 and UHF is 300 to 3000. HF is 30 to 300 megahertz. So all of these are megahertz.
Even. Oh,
Will you say that again, Scott?
yeah.
Okay. Where did it go? I must have closed it. So back on, let me go pull that up. It's, oh, where did I put it? The spectrum. Okay. Now we're going to share that. Sorry, I got to hit share again. Okay, everybody remember this?
Yeah.
Okay, here we go. There you go. The HF is 3 to 30. VHF is 30 to 300. UHF is 300 to 3000 megahertz. And now we look over here and you will find, what are they called? There's VHF, there's UHF, and down here there's HF. So you know that HF is 3 to 30 megahertz. And in fact, you could also correlate that by knowing that you have your 10 meters and you could say, okay, well, what's 300 divided by 10? And you know the answer's in megahertz. Does that make sense?
Yes and not.
What part not? Let's just hit it while we have it.
Sorry. So sorry. It's all the 330, 300, 3000.
That's just memorization. You just have to memorize it.
Okay.
I mean, that's the only way to know it. You
Okay.
just have to memorize
Can
it.
you put the band plan back up one time?
Yep. Okay.
What is between 24,990 and 28? Why is that on the plan?
Because it's not a ham band for one thing. Now, if we wanted to go see what it was, that was one of the things that you guys asked me to send you. And here it is. You guys asked me to send you this and I did. And so between, let's say, between 3 and 30 megahertz. Okay, let's see. And there's 24.99. Okay, so there's, notice it says amateur and amateur satellite right here. It's this stripe between 24.89 and 24.99. So 25 megs, we've got standard time, then land mobile, maritime mobile, fixed, radio astronomy, broadcasting, maritime mobile, land mobile, fixed, mobile, fixed, land mobile, and then finally we get to another ham band, which is between 28 and 29.7.
So we cannot operate on those at all.
Nope. We have no privileges there.
By land mobile, would that mean like that had been purchased by Verizon or AT&T or something?
It could be used by government. It could be used by any number. Russ, are you still here, Russ?
Yeah, more likely private companies. Like if UPS had radios in their trucks, that would be land mobile. Or and fire and police, I think, are on the same thing though too, although they're a little bit different.
Yeah, but I think the allocation is the same. I
Yeah.
think they're all considered that. So yeah, that chart that you guys asked me to send you, that gives you a full picture of the whole spectrum. What we're looking at when we look at the amateur spectrum is only the part of it that we care about because we're not allowed to be anywhere else.
Do the radios even let you go on those channels?
Oh yeah, you can receive them. You can receive, but more than not, unless you've modified the radio, you can't transmit there.
Yeah, most digital radios lack them out. Even the Baofangs lack them out.
Yeah.
But there's ways to, you can reverse engineer.
Let's say you have a reason to work with Mars, which is the military affiliate radio system, which operates outside of the ham bands. It's like a special permit that you would get. It's another exam that you take, and then you're allowed to participate with the military. Right adjacent to the ham bands, you would basically actually then get your radio modified to operate out of band. But once you do that, then you have a special piece of equipment which you have to take care of in a very special way, because there are then lots of ways that you can get in trouble with it. So
So
okay.
Scott, on
So
the
if
band
you
plan,
go down-
160 meters is technically not HF because it's below 3
That's
megahertz.
right. It's actually MF. That's right. It's actually in the MF band, medium frequency.
Okay.
Okay.
So
Yeah.
160 is operating at 2 megahertz.
Correct. And it's actually below the limit for HF. It's actually medium frequency. Behaves very differently, actually. Okay. Proof of possession of an FCC license. It must appear in the database. Yeah, that FCC database. Who can select a desired call under the vanity call sign rules? Anybody who has a license can apply for a vanity call. Now there are groups of call signs that you're eligible for. If you have a technician or a general license, you can apply for a 1x3 or a 2x3. And when I say this first number is the number of letters before a digit. There's always one digit, and so it would look like that, or it would look like this. You do not actually have to live in the same call area as the call sign number that you get. My wife lives in Oregon, and she is K3LUX. She lives in the 7th area call region. She has a 3 call sign because she wanted it. So one of my friends here, the Jim Fenster maker, he has a 9 call, but lives in Oregon, or he actually lives in Washington. And I have there's a guy whose call sign is N0RON down here in Eugene. His name is Ron. He liked the call sign, but there was no N7RON available. So he did find that there was a 0. So now he's N0RON. This is only really confusing. Yeah, no, Ron.
The numbers, Scott, the numbers refer to geographical location?
They do.
1, 2, 3, so on.
Yep. And
They refer to it, but you don't need to use them. And you can put
Correct.
in different geographical location numbers.
Yes, you can pick
So-
anyone that you want.
So,
However, when you get a sequentially assigned call sign, so once you take your exam, the call sign that you get will have the number that's assigned to the region that you live in as your address.
if you don't have a vanity one, then it will reflect your region.
Correct.
Okay.
The grace period for a call sign is 2 years. It's also important to note, and people sometimes ask me this, well, I put in something that my name is Mark, and I put in for M0ARK, and they wouldn't give it to me. Why not?
Because the person that had it before the grace period is
Nope.
not.
What's M?
Better tied to what kind of license you have?
Nope. This is not a US call sign.
Already been used.
Oh,
It's
it
not a
needs to
US
be a-
call sign.
Oh,
It's an English call sign.
It's a British call sign. We are assigned call signs that begin by this is by the ITU, part of the UN, WNK, and anything starting AA through AL only. Anything else is not a US call sign, and you cannot be assigned it. If you apply for it, they will laugh and say, sorry, can't do it.
what's the N and the AA? I thought it was just W and K, east and west of the Mississippi.
And that's only for commercial stations.
Oh,
And in fact, if you look the next time you fly anywhere, you will notice that the aircraft that you fly on will typically have a call letters that starts with the letter N. And I'm sorry, we are running a couple of minutes late. We should be done in about another 10 minutes. So basically there's that N. And so you will have like N3662A. That will be a United States flagged airplane. Interestingly, if you go and find another country, an airplane from another country, that N will not be an N. It will follow the same call sign prefixes as the radio call signs. Okay, let's see. A club, a club has to have at least 4 members. Once your call sign, if your call sign expires, you have a 2-year grace period to get it back without having to retest for anything. You are not allowed to transmit if your call sign has expired and you're in the grace period.
is that, you're using call sign synonymously with license?
No, a call
No?
sign, a call sign is something that's a part of a license.
Okay.
So yeah,
Because isn't that all the same information as would be true for license?
yeah,
Okay.
basically you're not allowed on the air until your
Right.
license is valid again. If the FCC tries to get a hold of you and the mail is returned as undeliverable, they can cancel your license.
Okay.
Because they assume that you are no longer present. When are you allowed to operate your station in a foreign country? That's whenever the other country says yes. And you can use your FCC license on any flagged, on any United States flagged ship, so long as the captain is good with it. So if it's in international waters and the captain is okay with it, and it's an American flagged ship, that's basically American territory. When are you allowed to use obscene or indecent language? The answer is never. When are you allowed to transmit music? Because we are a non-commercial service. There's only one time, and that's if you happen to be waking up the astronauts on the International Space Station or playing a retransmission of the wake-up call. This used to happen on the international on the space shuttle. They used to retransmit all the broadcasts from the space shuttle, and the wake-up music was a part of it. And they used to broadcast that on the ham bands for people to listen to. When are you allowed to encode anything to hide a message's meaning? So even if you're speaking with another person, you're not allowed to use codes or ciphers to obscure a message's meaning. The only time you're allowed to is if you're trying to control a remote control craft or a space station like a satellite so that nobody crashes it into the ground.
So wait, no kind of music can be transmitted except for your exceptions?
Yep.
And is it because they would take up too much time and space? And
Nope. It's because we have music stations that are set up to do that. We are not a commercial music service.
can you
So-
sing to someone on a,
Nope.
as you're giving a message?
Although that's a little more iffy. You know, I've heard people do it, but
What about
typically,
happy birthday?
I don't know. You could speak it. Happy birthday to you. Happy birthday to you. But you know, I mean, I
So you
think
can't sing either? You're not allowed to personally sing your own?
I don't. Yeah, maybe. I don't know. That's one for the lawyers.
The purpose of that rule is that we're not broadcasting, we're communicating.
Right. So it might be okay. I know for a fact that like one of our hidden transmitters, it goes,
Oh,
and that's okay. It's allowed to do a sequence of tones. It's not really music, but it's doing it. So I don't know. That's basically, we're not allowed to broadcast music. That's really what it comes down to.
Okay.
Let's see, when are we not allowed to talk to another station? Any country whose administration has notified the ITU that we're not allowed to. The United States has no standing agreements or disagreements with anybody that prohibits that. Even Iran, even North Korea. If North Korea were to actually have hams, we could talk. When is a teacher allowed to get, when is someone allowed to get paid to do ham radio? That's if they are a teacher and it's part of their classroom instruction. When are you allowed to sell stuff over the radio? Remembering that we're non-commercial, you're allowed to do that if it's once in a while and it has to do something with radio. That's why we can occasionally do a swap net on the air. Broadcasting is meant for the general public, just general information meant for everybody. One-way communications is meant for the amateur radio community. So you're allowed to do Morse code practice. You're allowed to do information bulletins, emergency messages. Hey, there's a wreck up at mile 226. The highway's closed in both directions. You don't expect anyone to reply to that. You're just giving information. When are we allowed to apply our skills to news gathering or broadcasting or program production? If the cell phone network doesn't work and we are with a reporter out at a dam and we have a live report, we're allowed to send it back, for instance, to the news gathering service over the radio. If it's about human life or protection of property and there's no other means available. Okay, so when are we allowed to, what are we allowed to transmit for one way? One way is code practice, information bulletins, and emergency communications. International communications, what are we allowed to talk about internationally? Basically, they say it is incidental to the purposes of the amateur service. That could be a lot of different things covered by those 5 rules, that why we exist, or communications incidental to the purpose of and remarks of a personal character. My sciatica is really acting up. Personal character. I do have sciatica. It's not much fun. We talk about it on the air. I used to laugh at things like that, but now that I'm older, it's part of who I am. So it's personal character. Okay, when are you allowed? Okay, so now we're into control operators and types, and we talked about this a little bit yesterday, and we're going to just get through this. There are 2 parts to your license. There's a station license and a control and an operator license. The station license licenses the equipment. The operator license licenses the operator. The station license has absolutely no privileges assigned to it. However, when you get a license, you will get both. So that covers your equipment and the person itself. So who is the control operator of an amateur station? That would be the station licensee. Basically, if it's your station and you've got the piece of paper or it's in the database, you're assumed to be the licensee. You're in control. Who must designate a station control operator? That's the station licensee. For instance, I am the trustee of the Valley Radio Club. It is a station license. If somebody wants to run it, I can say you're the control operator. If something goes wrong, who's responsible? And that would be both me and the person that I said was the control operator. So if, let's say, a repeater, which is an automatic station, puts out somebody cursing, or as we heard yesterday, somebody was playing a looped thing of some obnoxious thing on a tape loop for a minute, it's not my fault. I'm actually the repeater trustee. If I were responsible, I would be in a lot of trouble right now. But I can't control what goes over the repeater. It's the originating station that was actually violating the FCC rules.
that happened here yesterday?
That happened in Eugene yesterday for about 1 minute when I was listening. Just some random person with nothing better to do decided they were going to violate the FCC rules. And it didn't happen again.
Were they shut down right away?
I would have to be the one to shut it down, and I wasn't ready to shut it down at the time. It would have taken a couple of minutes to find the right code to shut it down.
You have a
How
code
could
that
you
could
tell?
stop them from transmitting?
I can shut down the repeater remotely. I have a back channel, a second frequency that I could actually kill the repeater.
You'd stop the repeater, but
I'd
could
shut
you
it down.
stop the
No, I
violin?
can't do anything to them. I can just make it so that nobody hears them. What the term?
How could you tell it was a tape?
Oh, trust me. Let's just say it was from let's just say it was probably a tape recording from a website of an adult nature. And
Oh,
the audio was somewhat obscene. I could tell. Yeah, you'd know. What do they say? You know, what's the definition of obscenity? Well, I know it when I see it.
Yeah, okay.
So, okay. What determines the transmitting privileges of an amateur station? That would be the class of operator license held by the control operator, the person who is in charge. So let's say that I am the control operator of a station and I have a technician class license. Is that station allowed to operate in a band in the extra class?
no.
Nope. Because now what if somebody else were to walk in with an extra class license? Say, okay, I'm going to be the control operator now. Then it would be fine. What if they left the room?
Can you do that? You can just switch
Yep.
whoever you want to be the controller at the moment?
Yep.
Oh,
And you can shut down the repeater from taking any frequencies that are not in a band you're authorized for?
Yep.
Wouldn't you have to use the call sign of the higher class licensee?
It depends on who is listed as the station trustee. If the station trustee has an extra class license, the answer is no. If the station trustee has a technician class license, then you would have to actually mention it, which is why most station trustees are extra class licensees, because you don't have to do that. Okay, who can be the control operator of a station communicating through an amateur or satellite or space station? Basically, if you're allowed to be transmitting the signal, even if it's coming down in a band where you don't have any privileges, you didn't put it there. So you're not doing anything wrong.
right.
So if you're allowed to transmit on the uplink, it doesn't matter where the signal comes down if somebody else put it there.
Okay, so the controller is only controlling what people are sending out.
The controller, I am only responsible for what I'm saying into this microphone.
Yeah.
What happens to it beyond that is somebody else's business.
For example, that repeater thing.
If it were a repeater in space, let's say that my repeater in space were uplink on 144 megahertz and downlink on 21 megahertz. Well, this would be technician and technician and up. 21 megahertz is general, advanced, and extra only. In other words, if I have a technician class license and my call sign suddenly appears on the downlink, well, somebody might say, well, you have a technician class license, your signal shouldn't be there. But the thing is, I didn't put it there. The satellite did. So that wasn't anything that I did wrong.
Mhm.
Okay, let's see. Amateur station control point. This is the control point right here. Right there, my push to talk button. This is an amateur radio station, just a simple handheld radio. Any equipment that is amateur radio equipment is a station. Automatic control, things that are automatic. A repeater is a perfect example of something that's automatic control because it's happening automatically. Part 97 defines remote control as operating the station over the internet. I actually do that all the time. I have a computer that's sitting right next to me that is normally sitting up in my station, and it is connected to my radio, and I log into my computer from somewhere else and I operate my station from somewhere else. One thing is that if you're there, somebody has to be there at all times. You can't walk away from your computer that's controlling it. So the operator must be at the control point. The control operator is always required and indirectly manipulates the controls. All right, we are in, yeah.
I don't think you just said that every repeater has to have somebody.
No,
there.
that is true because the repeater is automatic. However,
Okay.
in theory, a repeater operator should be available somehow. There should be somebody who is available to shut it down. Technically, I am the control operator, but because it's operating automatically, it's not remote, it's automatic. It operates by itself. That's a separate part of the rules.
So Scott, if someone is violating the FCC rule and it's going through our repeater,
yep,
should we set up a way in which the operator get notified so that we can shut it down, even if we are not listening to it?
You'll never figure out who it is. I mean, unless you can do direction finding, you'll never figure out who it was.
No, I'm not talking about who it was, but in order to shut it down, for example, say, if you had an incident where someone was violating it for like 5 minutes or so,
yeah,
but we are not listening to our station that we
okay,
are.
so there, first of all, the repeaters have a timeout. If the transmitter is activated for too long, it will automatically shut off.
Oh, okay.
That's the first thing. The second thing is you can't, but but unless somebody's listening, you're not going to know if somebody's violating the rules. So, all right.
How did you know that somebody was violating that other rule about inappropriate stuff? How did you know?
You can tell. I was listening.
Oh, you heard it yourself.
I was there. Yeah. In fact, they interfered with an ongoing conversation. So not only were they violating the rule that said that you're not allowed to do indecent or obscene things, they were also intentionally interfering with legally operating stations. So
but there's no way to report them.
Well,
you don't know.
Well, that's right. But then if they do it enough times, they really want to get caught. And then what you have is your repeater users in different areas will actually be able to use their direction finding skills and triangulate them and figure out a general area. And once you figure it out, you can pretty much find them.
Oh,
if they're repeat offenders. It's not hard to do. Okay, let's see. We're on to the very last page. When's an amateur station required to transmit a call sign? Every 10 minutes and at the end of a conversation. You actually don't have to do it at the beginning. When are you allowed to transmit without your call sign? If you're controlling a model craft like an RC car, if you are doing that, your transmitter has to have your name, call sign, and and I believe your address etched in a plate that's actually mounted to the controller, because you're not expected to actually transmit the call sign. What language do you use to identify your station? English? Even if you're having a conversation in a different language, you identify in English. You can also use Morse code in the background to identify your station. The phonetic alphabet. The phonetic alphabet is, again, Alpha, Bravo, Charlie, Delta. That's the international phonetic alphabet. It is used to, it's encouraged and used to simplify basically allow people to understand you better. Let's see, tactical call signs, race headquarters, aid station 3, you're allowed to use those. But what's important to remember at the end of the day is, are you a ham operator? Yes or no?
Yes.
Yes. What does a ham operator have to do every 10 minutes and at the end of a conversation? Call sign. That's right. So even if you are aid station 6, you can say aid station 6 out. This is aid station 6. Aid station 6 out. You talk and talk and talk. Every 10 minutes, and at the end, you actually have to give your call sign. The rules don't change. If you're operating in a different area of the United States, for instance, I might say that my call sign is N7JI/8, which means that I'm operating in Ohio. I could also say slant or stroke or slash if I'm using voice. Now, this is a self-assigned thing, the slash afterwards. If I were to say that my call sign were CE5/N7JI, that would mean that I'm actually operating in another country. I actually have a license that's been assigned to me temporarily by another country. And actually this would be Chile, which I've actually done. It's a lot of fun. Third-party communications. Anybody who has never had a ham radio license revoked by the FCC can operate as a third party if third-party communications are legal from the place you're talking to the place another person is. So if I'm in Oregon and I have a friend who's in California and we're talking back and forth and I want to put, I'm in a museum station and that other person's in a museum station, I can let a kid walk up to my station and talk to a kid who's down there in that other museum. They can have a communication. I and the other guy are responsible for what's going into the microphone, but basically those third parties are allowed to exchange information, and that's known as third-party communications. There are certain countries that we're allowed to do third-party communications with. There are certain countries that we are not. You just have to know those before you do it. And if the FCC knocks on your door, you have to let them in. If they want to see your equipment, you have to let them see it. If they want to see your documentation, you have to let them see it.
What documentation?
It might be manuals for your equipment. It might be the fact that you did you printed out a safety thing, RF safety exposure test or something. You might have that.
Okay.
They
keep it all in your logbook.
That's right. Just keep it all, or have it on your computer, able to show them, be able to print it out. So
has that ever happened?
I have never had it happen in 35 years. You've got to, honestly, you've got to do something pretty egregious to have the FCC knock on your door. Because how much does it cost at this point up until next month to get to apply for a license?
$15.
Well, no, it doesn't. That $15 is for the exam. That doesn't go to the FCC.
Oh, I just was incorporating it. Okay.
Yeah, no. How much money does the FCC get from us?
Nothing.
Nothing. That's right. And in fact, by virtue of that, they don't want to spend any money on us either. Well, that also means this is another reason why our frequencies are always under attack, because other agencies are willing to pay. Companies are willing to pay for those lights, for those same frequencies that we use for free. So our main job is to get out there and use what we have, use our equipment, use our skills, and make good.
I left the meeting
on the agreement that we have. So, any other questions? I'm sorry I took a little bit of extra time.
I have an equipment question.
Yep, go for it.
I was wondering if anything kind of jumped out at you, like as with your background, as far as anything that presents like a good, say, value for money proposal, like proposition as far as equipment.
Well,
like,
I mean,
I'm not trying to get away with like the cheapest setup I can get, but like I don't want to spend the moon either. So I guess I'd
hold on. Let me just mention this. By the way, tomorrow we've got the exam at 2:30. That also leaves tomorrow morning, which I'm not slated to do anything that I'm aware of tomorrow morning. So if anyone has any questions and wants to get together tomorrow morning to go over some things again or ask anything, I'm going to send out like a little note to everybody that says that at 9 o'clock tomorrow, I can be around, and we'll just have like it's a study session basically, in case there's anything you want to go over. Kind of like a free form thing. So, okay, Greg, to answer your question, how much are you looking to spend and what license, what are you looking the real question is, what are you looking to do?
Oh, hi, Jeff. Well, it says restricted.
I mean, I guess I'd be comfortable spending kind of in the $300, $400, $500. Like, I guess I just don't want to, like, so I bought a couple of the Baofangs just, you know, just to
have.
get something to play with.
Right.
But
what do you want? But the question that I have is, what do you want to do?
Well, you know,
and part of it might be, I don't know what I want to do yet.
I guess that's true. I don't really know. But I guess it'd be kind of nice. Like sometimes we'll go do some sort of Eastern Oregon overlanding out there, and it'd be kind of cool to have like sort of a backup comm system out there.
But I mean, are you looking at VHF? Are you looking at getting a general license or an extra license eventually and doing more? Are you looking at basically just having a backup communication system? Are you looking at doing digital stuff? A lot of it, a lot of what you end up with is going to be defined by whether or not you just want to, what you want to start with and where you want to go. And part of the problem is you may not know that. I mean, this is a very, very, very big hobby, right? There are people I know who just barely scratch the surface, and that's enough. And there are people that I know who, start very, very small and end up finding something that they really, really like doing. But you don't know that you're going to really, really like doing it necessarily until you're actually doing it and exposed to it. So,
I guess in the short run, I would think I'd like to get something that I could mount in my truck. But maybe if I got into it, like put a big antenna maybe in my attic, so maybe something that I could pull out of my truck and bring inside.
Yeah, you probably wouldn't want to move it.
Maybe get like a dedicated home setup then.
Yeah. Well, I mean, and that's where you look at, okay, well, and that's where you look at something like, I'm going to share this now if I can find it. Here we go. And we're going to go to a ham radio outlet just for the fun. Just for fun. All right. So if okay, in my car, I do not feel the need to have anything really expensive. So I've got it's FTM-3200, I think is what it is. Maybe it's an FTM-3100.
That's where you join the clubs and talk to other people, and sometimes they'll have presentations on different parts.
Yeah. All right. So this is exactly what I have in my car. Right. This is, yeah. And sometimes, and if you get them secondhand, or you find it at a ham fest, or you find somebody in your club who doesn't want theirs anymore, or sometimes they'll just be on even a better sale. I mean, you get one of these for $120, and okay, that's a 2-meter only radio. I mean, this is a very, very, very solid radio. I mean, I've had mobile rigs in my car that, it made it all the way down to 10 below zero. And in the summer in the car, it was 155 degrees. And I've never had a lick of problem with any of them, with any mobile radio that I've ever had, because they're designed for that, and for an antenna, I mean, it would just be something like this. I mean, you could put on you could have a permanently mounted antenna, but let's see.
I have a question for you.
Yeah.
On that radio, you said you went to 10 below. Did the display disappear?
No, it was just a little lazy.
Okay.
So, but here, something like this, right? This antenna, it's $29. And actually the antenna that I got was smaller. This is actually a dual band antenna. Notice it covers 144 and 430 megahertz. It's got that thing in the middle that's basically like a loading coil, or actually that's probably a trap, which allows it to operate on 2 different bands by essentially ending the antenna, because it's an LC circuit, by ending the antenna for 430 megahertz at that lower part. So it looks like a short antenna at 430 megahertz. Oh, look, it actually lists the gain, 2.4 dBd actual gain, 4.5 dBd on UHF. Oh, it's 5/8 over 5/8. Okay. That's actually a pretty nice antenna. And
That
notice,
radio would only be able to use the 2 meter portion of that.
right, but you'd also be able to, if you got a dual band radio, that same antenna would work for it.
Gotcha. But that 2 meter band is probably where a lot of the action is, right?
It is. I mean, 2 meters is kind of like the workhorse. And so like this right here, this is actually what I paired with my, with my mobile radio. And it's just a mag mount. It just sticks on the roof. And I have a semi-permanent installation on my car. Notice you get something from Bing Fu for $20. And this is where you start to get into, you know, maybe the antenna is not as strong, or maybe it's a crappier piece of coax. So then, you know, at some point you get what you pay for.
Gotcha. And really, in this kind of price bracket, I would just always go with the better one. Just, I mean,
Probably
$10.
so. Yeah. And like, let me stop recording before I forget. And